마이크는 여기
아, 네,
있나요?
Mic test, mic test. Does it work? It sounds good, right? Great, thank you. Closer? Is that better? Good, okay. Test, test. That sounds good. Sounds good.
Good morning, everyone. Welcome to the second day of Kavli Asian Winter School. I think we're going to start in probably 3 or 4 minutes. I understand there are still some people having breakfast. Okay. Okay, very good. Okay, the first lecture this morning will be given by Chris Akers from MIT, and his topic is black holes and quantum error correction. So
Thank you
please
very much.
start.
Thank you very much. And thank you for inviting me to give these lectures. So, yes, this is ultimately the topic of these lectures, and we will get there. There's an interesting connection between these two seemingly very different things. But first, I would like to start with some very general questions. What happens near singularities in black holes? Do black holes have firewalls? And in what sense and how is space-time emergent in quantum gravity? These are all interesting questions that people have raised in the field of quantum gravity, and we still don't have precise answers to. And one exciting thing about ADS-CFT, this duality between anti-de Sitter space gravity and conformal field theory, is that it offers a direct route to answers to questions like these. And the route is sort of a three-step process. So you might say, okay, first, formulate your question in gravity. Like, what happens near the singularity of this black hole that's in ADS? And then second, you could map that question to the CFT. So for example, in the first one, when you want to ask what happens, like if there's a firewall at this black hole, you could ask about some operator at the horizon of the black hole that measures if there's an excitation. And then the second step would be to map that operator to some operator in the CFT and evaluate its expectation value there. So you map the question to the CFT. And third, you would use the fact that we in principle understand conformal field theories. Even if we can't right now compute every correlator, you could, in principle, answer your question in the CFT. So this is perhaps an in-principle method to answer some of these major questions about quantum gravity. So given that we have this clear step-by-step procedure, why, ADS-CFT was discovered 25 years ago. Why didn't we just learn all of the answers to these questions about quantum gravity 25 years ago? Why aren't we done with quantum gravity? Where's the bottleneck in these three things? And okay, maybe they're all actually a little bit challenging. So I would say number one, perhaps there are questions we haven't thought of to ask about gravity, but I wouldn't say number one is the bottleneck. We have a lot of good questions already. We listed some. So we have a lot of good questions about gravity. Finding good questions to ask is not our problem. And number three, I would say is perhaps not the main bottleneck, although we don't understand, say, how to take n equals 4 super Yang-Mills and completely solve it, how to write down every correlator that's not protected by symmetries. That would be nice, and people are working on that. But we're not, say, all working on that in the field of quantum gravity. And why is that? And that's because there's a major bottleneck at step 2. We don't fully understand how to map all of the questions that we have in gravity that say that you could formulate in ADS to the CFT, which is kind of interesting. So as I'll review shortly, we understand the basics of the dictionary between ADS and CFT, right? We can feel comfortable that they're dual on a very precise level, but nonetheless, we don't have the know-how to map every specific question we would want to ask, like, here's a black hole in this state, is there a firewall at the horizon? We don't know how to map that to a CFT question very precisely. So there's a lot we don't understand about step 2, the dictionary between ADS and CFT. So in some sense, while this is going to be the topic, the sort of interesting new part of these lectures, this lecture series is going to fall under the bigger umbrella program that I might call bulk reconstruction. This is the name that's been given to it, where this just means the idea is that you're given the CFT, say, and that's the CFT is thought to live on the boundary of the ADS spacetime, and you want to reconstruct all the physics of the ADS, of the bulk. So given the CFT, how do you learn everything about the ADS? So this is a phrase that's thrown around about this program. So our idea is we want to understand the ADS CFT dictionary. And I would say dictionary is really the right word here, because in some sense, ADS physics and the CFT physics are sort of two different languages that we want to understand precisely how to translate between. And so these lectures are to explain to you much of what we know about, say, which operators in the ADS can be reconstructed on the boundary and how to do it. So let me mention there, sort of tangential point. There are actually, it's an active program to find exact schemes for reconstructing these operators. And I'll mention a few, but I won't be too concerned with how exactly to write a precise equation for an operator in the CFT that is dual to an operator in the ADS. Instead, my focus is going to be about these theorems about what is generally possible and not possible in principle. So we're going to see which operators in the ADS can, in principle, be reconstructed in the CFT and which cannot. So I think that'll make more sense as we go along. Okay. So to start this discussion of the ADS CFT dictionary and what we know, I'm going to sort of take a quick historical path to see what progress has been over the years up till about 2015, and then we're going to spend a lot of time talking about results since 2015, 2016. So let's start with the basics of ADS, so we're all on the same page. We're going to talk about the basics of ADS, and then the basics of CFT, and then the fundamental statement of the dictionary, so we all know what the starting point is for this discussion. Right, so in gravity, we care about spacetimes that are solutions of Einstein's equations. Let me write them down. Of course, all of you know them. So here is the cosmological constant term. This lambda is the cosmological constant. This T mu nu is the matter stress tensor. And ADS, anti-de Sitter, is the maximally symmetric vacuum solution with negative lambda here. Lambda is a constant. And vacuum ADS has this metric. Write it this way. It won't be very important for these lectures that you understand the details of this metric, although I'll say some things. It's just here for completeness, really, so you understand what we're talking about when we say ADS. So in this metric, t is a time coordinate, runs from -infinity to infinity. R is a radial coordinate running from 0 to infinity, and this is the round metric, the sphere in d-1 dimensions. So this metric has little d spatial dimensions and 1 time dimension. So it's a d plus 1 dimensional space-time. And you might, and this little l is often called the ADS radius. It's related to the value of lambda. If you want, lambda is related in this way. It's like d times d-1 over 2l squared. That's just how it shows up if you solve Einstein's equations here in the vacuum. And the diagrams we often draw for this, these diagrams will be important because I'll draw them quite a lot. So it's convenient to draw it like this. It's like a cylinder. This is a sort of compactified way of drawing it, because really there's infinite spatial volume in this metric, but I've drawn, say, this disk right here is one spatial slice. So this is, say, one slice of the cylinder. So the cylinder is supposed to go all the way, infinitely high up and infinitely far down. That's the time direction. And then the r direction is here. So the radial part of this disk, say. And really there's infinite volume, but we've drawn it in this compactified way, which is very convenient for talking about ADS. And ADS has very interesting physics that I won't delve into because it won't be important for these lectures right now. But what will be important is, well, let's say we take this time slice and we just draw that. It would look like this circle here. So this is a time slice. So I've just taken this cross section, or this disk, and drawn it here. And so R, say, is running out this way. And again, there's infinite volume here. And this is a curved space-time. And so straight lines don't exactly look straight here, right? So if a geodesic, say, starting here with that initial direction would do something like this in this geometry. And we'll come back to that. That will actually show up later. Now, this was the vacuum solution to Einstein's equations, and this is what's technically ADS. But when we talk about ADS-CFT, despite the name, we generally care about these gravitational solutions that aren't exactly ADS. They're more asymptotically ADS. They approach this metric at large R. So this includes, for example, solutions where there are black holes in the bulk. The bulk being like the interior of the cylinder. So I'll often say bulk, of course, when I'm talking about the ADS spacetime. And so, for example, let me try and squeeze it in on this side here. There's the ADS Schwarzschild solution. Let me see if I can spell it right. Which is also a solution of Einstein's equations with negative cosmological constant, but now that instead of having zero mass zero total energy, it has total energy m, which you might think of as the mass of the black hole, and the metric is something like minus f of r dt squared plus dr squared over f of r plus r squared d omega d minus 1 squared. Sorry, it's getting a little crammed here. But this f of r, in this case, looks something like this. Again, the details aren't super important. I'm just writing it for completeness. This is 1 plus r squared minus, let's say, 16 pi g m over d minus 1 omega d minus 1. And there's a 1 over, sorry, this is really crammed. Let me write it here. In this denominator, there's an r to the d minus 2. Sorry, that's very crammed. This is an r to the d minus 2. And you can confirm to yourself that, of course, at small r, this is very different from this ADS metric, but at large r, it approaches this one. So they in this sense have the same asymptotic boundary, but they're different in the interior. And that's going to be important because the CFT they're dual to, we imagine, is living on this asymptotic boundary. So the CFT can have different states. One would be the vacuum solution, one would be this black hole solution. Sorry, they would be dual to the vacuum or dual to the black hole, but the CFT itself, in both cases, would live on the same space-time, because the boundary here is the same. And as I will come back to, Penrose diagram for this metric would look like this. So here, if you draw this, so here we actually analytically continue the coordinates. So r doesn't go just from 0 to infinity, but actually it goes in both directions, minus infinity and infinity. And so this metric matches that one, and the r to infinity limit, which so this line right here is that asymptotic boundary. This line is a second asymptotic boundary, and so both of these boundaries are actually, in the bulk, connected by a wormhole. So these wiggly lines are the singularities of a black hole and white hole, respectively. This x is the event horizon of these black and white holes. And if you say, looked at this bulk time slice, the geometry of that would sort of look like this. So I'm going to draw it down here. Sorry, it's getting very squished. But it might look like this, where this circle here is like this circle, right? It's the circle at one of the boundaries. So there's two circles, these two asymptotic boundaries, connected by this bulk time slice. So this is a wormhole passing from one side to the other. Okay, so these are example ADS solutions that we'll talk about. So we will care a lot about black holes, and not just these black holes that are solutions with T mu nu equals 0, but perhaps black holes that form just like those in our universe from stars that collapse, which you can form by, say, taking this metric outside the star and some collapsing star metric, and you glue them together, and you'll get other solutions. We'll come back to that when it's important, but roughly speaking, we have these ADS metrics, and so far we've discussed what the geometry is doing. But besides just gravity in ADS, the theory in ADS can also contain matter, which we'll treat as a quantum field theory living on curved space, perturbatively coupled to gravity. And this sort of theory we call semi-classical gravity. So if I say semi-classical gravity, I'll mean we have, say, one of these metrics with quantum field theory on it, and that quantum field theory is perturbatively coupled to gravity. Yeah, hope that's clear. So there will be operators, say, maybe there's like some scalar field living in ADS, and there'll be some operator like phi, and we might be interested in evaluating phi. We might want to do it using the CFT, which I'll talk about right now. So these are the sorts of questions that I'm trying to set up here. So we have this ADS theory with operators, and we want to map those operators to CFT operators. So let's discuss the CFT. Okay. So, right, CFT basics. Many of you are experts in CFTs. Let me just say the very, very basics that will be used later. So CFTs, conformal field theories, are relativistic QFTs that, in addition to Poincare invariance, have invariance under some new transformations, dilations, and special conformal transformations. And dilations are transformations of the coordinates that look something like this, where this is x mu prime. So you had x mu, and then we're defining new coordinates related as follows: lambda times x mu. And special conformal transformations are defined, say, by a coordinate transformation that looks like this. And these transformations have generators. So we'll call the generator of this one D. I'll use it momentarily. This one I won't use, but the generator is often labeled K mu. And together with the Poincare generators, these form the conformal group SOD, 2. This is a D-dimensional conformal field theory. And local operators transforming in representations of this conformal group satisfy this equation. So if O of x is a local operator in the CFT, or that transforms in representations of this group, it would satisfy this equation for some delta. So here we're just taking O, and we're transforming it under a dilation. And what we get is something that's like O, but multiplying this e to the alpha delta. So this delta is some number that's called the scaling dimension of O. And that's going to show up momentarily in the statement of the dictionary. That's why I'm writing it there. So the scaling dimension is important. It's some important data about the CFT. The scaling dimensions of its operators. It's important data. So this is the lightning intro to conformal field theories that will be relevant for us. And so as I alluded to but didn't say exactly, what's nice about conformal field theories is that they're UV complete. Like because this is a symmetry of the theory, as you zoom in, so if you had some state or configuration and you zoomed in, you got further and further into the UV. That's a symmetry of the theory, so it's still described by the same conformal field theory. So in that sense, they're UV complete. And that makes ADS-CFT very nice, because it's more than just the statement that this theory of gravity is dual to some quantum field theory. And in principle, we understand how to solve quantum field theories pretty well. It's more than that, because it's a special quantum field theory, a conformal field theory, which is UV complete. So in this sense, it offers a way of understanding the UV completion of gravity. Right? So in this sense, the conformal field theory can sort of play the role of the UV completion of gravity. You might think about it that way. So it's very nice that it turned out to be a conformal field theory dual to ADS gravity. Okay, so this is the lightning statement of the two sides, but now let me give you the perhaps fundamental statement of the duality. So we're going to start discussing the dictionary and what we know about it. So the fundamental statement, which is the first entry into the dictionary, is this. So the fundamental entry into the dictionary that I will discuss now goes by the name the Extrapolate Dictionary. And I'll explain why it has this funny name. Even though, I'll say it's fundamental to the dictionary, but perhaps it's not something that you would find directly in Juan's original paper or Ed's paper, but it's equivalent to what you find in Ed's paper, and that was proven later on. By the way, I'm going to give citations for all of these things in some lecture notes I'm writing up that I'll post and hopefully alert you then. But for example, the Extrapolate Dictionary in its current form was first written down in this paper in '98, so pretty soon after Juan's paper, by Banks, Douglas, Horowitz, and Martinique. And what the Extrapolate Dictionary says is how to relate some bulk operators to some ADS operators to CFT operators. And says the following. So you're supposed to imagine that you have, say this is a time slice of ADS. Oh, I didn't say this explicitly, but maybe it was already clear. So if this is a time slice of ADS, the CFT is imagined to live at the boundary of ADS, so on the can of the cylinder, so the outside of the cylinder. That's the manifold in which you might imagine the CFT lives, whereas the ADS lives in the interior. And so in a time slice, the disk here is the time slice of ADS, where the circle is the time slice of the CFT. And that's important for the Extrapolate Dictionary statement because, remember, R was this radial coordinate, and we might, say, have some bulk operators. Let's say we have these 4 phi's at some radial distance and some angular position. And we can ask about the 4-point function or some endpoint function. And maybe it looks like this. So let me write it like this. So there's a phi at R and, say, angular position x1. Or this will be space-time position x1. So x1 here is the position of phi and all the coordinates that aren't R. And the other phi is at, say, x2, R. So here it's at the same R, but possibly different in all the other coordinates, and so on. So let's say this is an endpoint function. So this is some ADS endpoint function. Now, we're going to relate this in a limit to a CFT endpoint function. That'll be the statement of the dictionary. And so what we're going to do is take a limit that, think I wrote something wrong in my notes here, but we're going to take a limit that r goes to infinity. So this is some endpoint function between operators, say, at different points, but now we're taking a limit that they all go to the boundary. And, sorry, I'm trying to correct the sign in my notes. So I believe what we have to do is multiply. If you just did this naively, you took this limit, then this would vanish, the fields die off. But we have to correct for that by multiplying by this r to the n times delta. And delta is going to be the scaling dimension of the dual CFT operator. So that same delta over there. But not for these guys, because these aren't CFTs, so they don't have a well-defined delta necessarily. But for the dual operator, which shows up on the right-hand side here. And so the idea is that every ADS field has a dual CFT field, and that the relationship between them is given by this equation. So there's, on this side, O of x1, O of x2, and so on, to O of xn. So this is in this precise sense, the CFT dual of phi. So for example, if phi were some graviton operator that was associated to the graviton, the O here would be the stress tensor in the CFT. And for other operators, say for scalar operators here, you have some scalar operator there, and this delta, as I said, is the scaling dimension of O in the CFT. So this is just an entry into the ADS CFT dictionary. And this, in principle, what's nice about it is it specifies the duality. But of course, there's a limitation here. So, right, in this equation, we had to take a limit where all of these operators went to infinity. So for example, if we were interested in some bulk correlation function between, say, like the 4-point function of operators phi here at infinity, we could get this, the leading behavior here in R, no problem. That's what this dictionary gives us. But if we were interested in something that seems like a pretty reasonable question, something like this, where the 4-point function is for points that are far from the boundary, this doesn't automatically tell us the answer. So it doesn't do that for us. So we're going to have, so if we want to use the CFT to evaluate things like this, we're going to have to work a little bit harder. Okay. So that, getting things like this, at least in certain backgrounds, like vacuum ADS, was addressed in 2006, and is what I'm going to turn to now on this board. So here we're starting to see the evolution of our understanding of the dictionary, how to answer bulk questions using the CFT. So this thing like in the bottom right there, where if you wanted to evaluate that 4-point function in the CFT, you have to work harder. What you have to do, at least in certain cases, was worked out by these people, Hamilton, Cabot, Lipschitz, and Lowe, and it's now called HKLL reconstruction. And the idea is this. So what they said was, okay, operators like phi have to solve the equations of motion, which is some PDE. And you could, in principle, solve this using, at least in certain cases, solve this using Green's function methods with boundary conditions at spatial infinity given by the extrapolate dictionary. So in some sense, you're solving the bulk equations radially to write a bulk field in terms of boundary fields. So what that looks like is they were able to write a formula like this. They said, okay, you have this 5x, or if I'm being consistent with my coordinates, you have like 5xr. So this can be for r that's not infinity. And this is a bulk field. And they gave some equation for it that works. Again, it'll be in certain special cases, which I'll discuss. And it looks like this. So you integrate over points in S of x, which I'll say. Capital X is going to be boundary coordinates in this equation. This little k with two arguments, little x and capital X. Really, this is little x, little r, and capital X. So this is the bulk coordinates that appeared on the left-hand side, and then these are boundary coordinates that you're integrating over, this capital X. And then this O of capital X is local boundary operators, local CFT operators at point X. So so this K is a kernel, and we're writing this bulk operator as some integral over local operators in the CFT. And it's not local operators at every point in the CFT manifold. It's only over S of x, which are, as I'll draw, they're points on the ADS boundary, so points on the CFT manifold, boundary points that are space-like to this point x, the bulk point. So so let me draw that to give you some intuition. So it looks something like this. So this is the cylinder that we draw ADS using. And we might have, let's say this point right here is this point XR. And so what you want to do to find this S of x, the bulk, the CFT points that you integrate over, is you just find all the points on the ADS boundary that are space-like to this bulk point. Now, I didn't dwell on this, so it might not be obvious if you're not very familiar with ADS, but even though there's infinite distance here, the light rays from this point actually reach boundary points sort of at finite boundary time. It doesn't take infinite time for them to get all the way to the boundary. It won't be super important. I'm happy to talk more about that, but maybe you're willing to accept that. So if I shade it in, so it's sort of all of these points in the CFT that you're supposed to integrate over in this formula. And okay, that was the at least first formula that they wrote down, but let me note here that actually you don't need to integrate over, you don't need this whole strip here in the CFT to write something dual to this operator. You can actually use just a single time slice, say like this time slice of the CFT. And the way that works is, so in any quantum field theory, not just a CFT or something, if you have, let's say this is a time slice, and later on you have some, say, O of x comma t, so that this acting here, so this is some local operator acting here, this vertical direction will be time, and then x is going to be sort of the left-right direction. And then this is some earlier time slice. You can write this operator as some operator down here on this time slice in the past light cone of this guy. So you can write this operator either as some local thing here or as some sort of non-local smeared out thing where this past light cone intersects this time slice. And it looks something like this. E to the I ht O of x comma 0. So this is O at the same spatial position, but at t equals 0. But I'm saying here that this is the t equals 0 slice, say. And then e to the minus I ht. And this is going to be some complicated non-local operator at on this t equals 0 time slice. But it'll have support in this region, the intersection of that time slice with the past light cone. And the idea is that when you act this operator at this time, it sort of just evolves you up in time and then acts the operator, so that would be here, and then evolves you back in time, so you end up on the same time slice that you started with. Yeah. Here, yes, yeah. For here, x is a spatial. Yes, thank you, yeah. Sorry, I was being kind of a loose, switching back and forth, but yes, thank you. Here I wanted to emphasize that this is at a different time, but the same spatial position. Thank you. So I just bring this up to say, even though this formula written this way manifestly involves an integral over local operators in this whole patch of the CFT, you could write it just as let me draw the same thing over here so it'll be less busy. So here's the cylinder again, and then here is that bulk operator that we want to reconstruct on the CFT. You could just use a single time slice, and the way you do that is you first use this formula, and then for every O that doesn't live on this time slice, you rewrite it using this as some complicated operator living on this time slice. So now this becomes a more horrible looking formula, but it has the virtue of living only on this time slice. Okay, so you can map operators at one time in the bulk to operators at one time in the CFT. And that's the nice thing. Okay. So good. So they wrote this formula, which seems like it allows us, at least in some cases, to write bulk operators as boundary operators, even bulk operators that are sort of deeper into the bulk, away from the boundary. Good. Is this everything we want? Yes. Can you say that again? How is the what decided? Oh, the kernel. Good, yeah. So it's related to the equations of motion of the bulk fields. Yeah, it's important. You basically have to be able to plug this into the equations of motion for phi and get something sensible, where I don't know that I could say much more detail about it right now. That's no, it does not uniquely determine. That's a great question. Okay, yeah, good. Thank you. Thank you for bringing that up, because so there are actually many Ks that work, and so for example, you don't even have to. It turns out you don't even have to use this K that maps a bulk operator to the entire boundary. There's many things. Many different Ks you could use. Some of them actually have this very interesting feature that you can map this phi, say, to just a CFT operator, say, with support only on a subregion of the CFT. So for example, what you're kind of doing is solving the equations of motion radially, like we said before. But instead of solving it radially in every direction, you can sort of solve it radially in one direction, and it becomes some smeared operator really it's you can write it on some boundary subregion for which the operator is in its causal wedge. I might say a little bit more about this momentarily, but I won't dwell on it too much, this sort of subregion reconstruction, because we're going to shortly see something even more powerful. But that's a great point. So this K is highly non-unique. There's many different Ks you can write down, but in fact, none of them are going to be as powerful as the reconstruction schemes we're going to see. So that's why I'm not going to dwell too much on it. Yes, yes. Can you say that again? Oh, is it consistent with this over here, or? Yes, yes. It limits this because good. That's a good question. Yeah. So in this, right, in this form, it's maybe not completely obvious because it looks like at all points it's using some integral over the entire boundary. I haven't worked it out myself. I believe that I would not be surprised if it just reduced to this in the limit, but like reduced to the having support only on one in the limit, although it's not obvious to me how that would work out. But say again? Yeah, that's a good question. So I think certainly if you use this sort of reconstruction, this like Rindler, this K that only has support on a subregion, that one I fully expect to manifestly limit to this extrapolate dictionary version. This K that has support on the whole CFT, yeah, that's a good. I'm sure it's consistent, but whether the limits manifestly match, I'm not sure. I would expect it must be consistent, but yeah, that's a very interesting question. Yes. This Hamiltonian here. So in the case of the CFT, it's the CFT Hamiltonian. So in general, this is just the Hamiltonian of the quantum field theory. Yeah. If you hand me the bulk phi, how do I determine O? Yeah, that's a good question. So, yeah, what's the best algorithm for this? So there's a lot of consistency data that has to be consistent between the two. Okay, so yeah, good. There's a statement that's equivalent to the extrapolate dictionary in which that is perhaps more manifest, where it's sort of an equivalence between the generating functionals on the two sides. So like the partition function with a source in the CFT equals the partition function of the bulk, where the source is now a boundary condition. And so if you differentiate, so in the CFT, it's clear from this formula what CFT operator is coupled to the source. So if you differentiate with respect to one source, it's clear what CFT operator you're pulling down in the correlation function. And then you have to look at if you knew this equality, the equivalence between the partition functions, it would be manifest. Because you could then just look at what field has its boundary conditions set by that source in the bulk. I'm afraid that might not have been very illuminating. Let me say another thing this way. So the data has to match very nicely. So you're right, they have to have the same. So the delta here in the CFT, the scaling dimension of O, is related by a very specific formula to the mass of the bulk operator. I forget it off the top of my head. It's something complicated with like a square root of delta times delta minus 2. And the spins match up. So like the graviton being spin 2 matches to the stress tensor, which has 2 indices. I'm afraid I can't give you a much more detailed answer right now off the top of my head on how to. One way you could view this is that the statement of the extrapolate dictionary is that you're promised that for any bulk field here, there is some corresponding boundary field here, and you have to find it, and it has to match in the sense that the mass of this field is related to the scaling dimension of this one, and the spin is related to the spin, and so on. So in some sense, all of the data you need about the CFT operator, like its scaling dimension and spin, et cetera, is just given to you by looking at the bulk operator. So if you knew the bulk theory and you knew it had a CFT dual, you could look at any particular ADS operator and then learn all the data about the dual CFT operator from those equations I've mentioned. Is that? Good. Oh, well, it doesn't have to be primary. Like descendant operators in the CFT also have some bulk dual as well. I mean, so it's like. So yeah, there's this one-to-one relationship between operators on both sides, and it won't. So even descendants and multi-trace things and nasty things in the CFT will all have bulk equivalence. Yeah. So we're requesting locality of some specific operator. I don't know if they can answer the question in real time, but.
Yes, so probably he asked we consider the bulk locality, at least approximately, or
Yeah.
how does it translate on the condition on the CFT?
Okay, this is actually a great question that's going to segue into one of the great mysteries we're going to try and answer with these lecture series. So one thing that this question is probably getting at is the fact that in the bulk we have this one extra spatial dimension. So it has this, locality structure associated to having d spatial dimensions. And nonetheless, we have some dual operator in the CFT, or we're supposed to. And these dual operators live in one fewer spatial dimensions, which has a completely different locality structure. So so the question might be asking, how do you get this bulk higher dimensional locality from the physics of this CFT lower dimensional locality? And that is a great question and comes with a lot of great mysteries, and that's exactly what we're going to try and answer with these lecture series. So I encourage the asker to hold on to their question, and then we'll get there. Okay, so yeah, we've seen that there's this sort of reconstruction. Is this everything we want? Are we done? Could we ask our questions from the beginning of this lecture series? And I would say, not really. We're not done. This sort of reconstruction is not powerful enough. It's too special. Let me give you an example where it doesn't really give us what we want. Good. So it works, not necessarily, yeah. So it works perhaps best and most cleanly there, but even away from strict large N, say when you want to include interactions perturbatively, like some 1 over N expansion, there is a way, or at least a proposed way for doing this. Now, whether that series converges, or maybe it's an asymptotic series that gives you some answer to some approximation consistently, that's a whole separate question. I would say that in general, this will not, away from this like strict large N and away from vacuum ADS, it's not going to give you a useful answer or any answer at all. And that's actually what I want to argue right now. But the short answer is yes, you can include interactions and go away from strict large N, but it's much messier and perhaps not as convenient. So this isn't everything we want, this HKLL reconstruction, because it does not appear that you can get Green's function solutions like this always. They don't generally exist. Right, like we're familiar with, say, in electrodynamics situations where we are promised that there do exist solutions more generally. But this is a different setup, because here we're solving the equations radially. So it's like a space-like Green's function as opposed to a time-like one. And so the promises about when such solutions exist are much weaker. And so, for example, here's a situation where it does not work. So remember our ADS Schwarzschild, where we had. So this is a black hole, and these dotted lines represent the horizon of the black hole. So a point here, for example, is inside the horizon of the black hole. So really, it's located somewhere in the wormhole connecting the two sides that are outside of the respective black holes, and it itself is doomed to fall into the singularity. So like if you were this point, right, your future light cone just forces you into the singularity. This point's inside the black hole. And what's problematic is that if you tried to consider some operator here, some phi, and use HKLL reconstruction or something like it to write this operator in the CFT. Here there's actually two CFTs, right? So this is a CFT right might live here, and CFT left might live on this side. The points that are space-like to this phi are the ones, right, that are in this wedge, or yeah, that are on this side and this side. So the problem is that because this phi is in the black hole, some of these points are hitting the singularity, right? So it's not like all points in the boundary, or all points that are space-like to phi are at the boundary. Some of them hit the singularity, and for that reason, that's sort of an explicit demonstration of the fact that you can't just solve the equations of motion for phi radially and get some operator in R. It hits the singularity. That's a problem. This Green's function solution won't work. Okay, so that's no good. And let me mention, so this relates to a question or point that was raised earlier. There's what's called Rindler reconstruction. This is the name that was given to it. So this is a version of HKLL reconstruction that doesn't use the whole boundary. So it's worth noting this because it's going to connect to where we go. So you don't need the whole boundary. Like a whole time slice, you don't need that. A subregion of the CFT suffices to reconstruct some ADS operators. So, right, so the drawing was something like this, or if you have some operator phi here, there might be some CFT subregion, like this one I've drawn here. Sorry, the drawing's bad. And you can actually find a kernel, K, in that formula that writes this as some integral over points just sort of in this shaded region of the boundary. And you can use that same trick over there where you evolve operators to one time slice to write it as some let's write this bulk operator phi as some operator O, some integral operator, local operators O, just on this subregion of this one time slice. And this goes by the name of Rindler reconstruction because you can do this for phi if phi is in the so-called Rindler wedge of this boundary subregion. The Rindler wedge is not going to be super important, but it's roughly what you get if you took this boundary subregion and you found its whole domain of dependence on the boundary, if you're familiar with that term, and then you found the causal future and the causal past of that domain of dependence in the bulk, and took their intersection. If this operator phi is in that intersection, then there exists a k that writes phi, at least in vacuum, that writes phi on this subregion of that boundary. Those details not super important, but perhaps it's helpful to hear them. And I wanted to bring this up because this is actually the first example of so-called subregion duality, where you can use a subregion of the CFT to reconstruct data about a subregion of the bulk. And that's very important, but I'm not going to, because we're actually going to discuss subregion duality quite a lot. But I'll delay the discussion of the importance of subregion duality until we've seen its more modern formulation. Good, yeah. So you get, that's a very good question. So you get an operator that is supposed to be dual to this bulk operator. Now, is it the same CFT operator that you get? That's a question. The answer is going to be no. But understanding why that has to be the answer and why that's significant is something I'll probably get to next lecture, which ties into quantum error correction. But so yeah, they both are supposed to reconstruct phi, but they're not supposed to be the same operator in the CFT. So that might be kind of mysterious, but that's an important mystery, and we're going to solve it. Can you say that again? So there is a way to determine that CFT operator. Yes, at least there is a way to right. So like this formula like K is known, and like say if you had vacuum ADS and you had some subregion of the CFT, some say spherical subregion of the CFT, and you had some bulk operator that was in its Rindler wedge, you could write down this formula exactly, like in the strict Largen limit. Like that's completely known. I'm just not writing it here. And and you could compare the reconstruction you get in a subregion to the reconstruction you get globally, and see if they're the same. And the answer is they generally won't be. Maybe that's what you're getting at. Yeah. But it's more than just a like coincidence. It's actually surprisingly deep that they're not the same. I think that's what I was trying to say, and we'll get to why it's deep. Sorry, this thing is very loud. Can you say that again? Good, yes. Thank you for bringing that up. So yeah, here, when I drew this picture, I said I drew it like we needed to push this guy to both the left and the right. But for this reason, you could, let's say, yeah. So you could say, what about this operator here? Naively, if I had to push it to the left and the right, I would have the same problem because trying to push it to the left, I would hit the singularity. And it turns out to not be a problem for the reason you're getting at, because of this. Because you can do Rindler reconstruction, it would suffice to reconstruct this guy using just the right, because you could push him just to the right side, write him as an operator just in the right CFT, and then you'd be safe. So in the black hole case, things outside the horizon can be reconstructed in the CFT. Things inside can't in this way. So yes, thank you. That's a great point. Good. Good. So having said this, we see that there's disappointing examples like this. So this reconstruction scheme doesn't work in all the cases we might want. We would like a reconstruction scheme that works as generally as possible. And it would be nice if it wasn't just more powerful than this one, but if we could prove that it was as powerful as anything, that there was not a more powerful scheme. That would be great. And in fact, we now have the ability to do that. So we have theorems about what you can in principle reconstruct, and using the CFT, and that you can do this, but you can't do any better. We have theorems that say things like that, and that's where I'm going to turn to now. And so I'm going to go over here. And for getting these theorems that tell us these very surprisingly powerful things about what you can and can't reconstruct, our best tool has been the so-called quantum extremal surface formula. And for many of you, that's a very familiar formula. But let me review it, because it's going to be maybe the star of this lecture series. So it's the quantum extremal surface formula. Sometimes called the quantum extremal surface prescription. QES is the acronym, so I might say the QES formula, or the QES prescription. And okay, so now we view this as this amazing formula that tells us everything that there is to know about bulk reconstruction, because we have these theorems that tell us that. But it didn't start life that way. It had more humble origins. It was just supposed to be a formula that allowed you to compute von Neumann entropies in the CFT using the bulk. And so let me tell you, the precise statement. So the precise statement is the following. So first, recall that the von Neumann entropy is defined as the following. So let's say you have some Hilbert space HB, and then on this Hilbert space you have some density matrix rho. The von Neumann entropy is defined by this, so I might write it like this. So this S of B with the subscript rho is saying the von Neumann entropy of system B with this Hilbert space in the state rho, it's given by minus the trace of rho log rho. And what the quantum extremal surface formula says is that, let's say, the setup is the following. So again, I'm going to draw our cylinder, and then we have, I don't know, say this circle here is a time slice of the CFT, and we have some subregion, say this subregion here, this shaded one, we'll call that B. And then the complement on this time slice might be B bar or something. And what we might be interested in is the von Neumann entropy of this subregion. And, okay, so caveat, strictly speaking, CFTs are, these subregions of CFTs are best described by von Neumann algebras, these infinite type 3-1 von Neumann algebras, and those don't have density matrices. I'm going to ignore those subtleties. Everything I say can be generalized to that language, but it makes it much more complicated, and the basic idea is well captured by assuming that, like more mundane quantum systems, there is some density matrix associated to this subregion B that describes the physics there. So I will make that assumption quite a lot. So the idea is that you can compute the von Neumann entropy of the subregion B in its state rho using this formula, that it equals, so here I'm actually going to write rho with a subscript CFT to make it very clear that we have some CFT state and we're trying to compute the von Neumann entropy of subregion B in that CFT state. And it equals this, well, what we'll say is A of B over 4G plus S of little b. So I haven't told you what little b is yet, but I will. And then this is also, it's itself a von Neumann entropy evaluated in the state rho ADS. And so rho ADS is the dual ADS state. So part of the ADS CFT dictionary is that if you have a CFT state, there's an associated ADS state. So you're supposed to say, start with the CFT state, find the ADS state that's dual to it, and that's what goes here in the formula. This A of little b is the area of some surface. So what is little b? Well, little b is some bulk region. So there's some, so what you're really supposed to do is find, there's going to be some surface, who I'm going to define for you. Let's call it gamma. So it's some surface homologous to this boundary subregion. And that homology region, bounded by gamma and capital B, we're going to call little b. And so if I were to draw a time slice of this, I'll draw it over here. Right, so this is the time slice that I drew, and maybe capital B was this region here, the shaded region. And the interior of this disk might look like this, where this is the surface gamma that I drew here, and little b is this region between gamma and capital B. And so there's some ADS density matrix associated to this region. The von Neumann entropy of that density matrix is this guy. And then the area here, this A of little b, is the geometric area of gamma. So this formula holds if, and only if, this is the statement here, it holds if B is, or if gamma is the minimal quantum extremal surface homologous to capital B. So a quantum extremal surface is one that, first of all, extremizes this quantity. So this quantity, A over 4G plus this entropy, that's called the generalized entropy, area plus entropy. And gamma, for this formula to hold, has to extremize this. So if you did local perturbations of gamma, it needs to be extremal under those local perturbations. So this quantity should be extremal if you varied gamma under locally. And moreover, if there are multiple such surfaces that all extremize this quantity here, the one that satisfies this formula is the one that minimizes this quantity among those extremal guys. So gamma has to be the minimal the minimal quantum extremal surface. Quantum extremal might be a weird phrase for some people. So an extremal surface would be one that extremizes the area. Quantum extremal is supposed to be one that extremizes area over 4G plus S of the region to one side. So this formula is very nice because it allows you to, say, take this CFT subregion, and it might be, in general, hard to compute its von Neumann entropy, but you can do it using this formula if you use the dual bulk state. And this formula has a very storied and impressive history. So it was originally, its original incarnation was given by Ryu and Takanagi, called the Ryu-Takanagi formula in 2006. So I'll just note here some historical details. Started with Ryu and Takanagi in 2006. And there, it did not include this term here, and you're minimizing just the area part, and it was supposed to give you the correct answer in some expansion in 1 over g. So g is supposed to be small, and since then, so this was a very important formula in the history of this field, and since then, the Ryu-Takanagi formula has been built on and derived from the ADS-CFT dictionary, and its final incarnation. So there's many steps along the way. I don't mean to leave people out, but Engelhardt and Wall in 2014 first stated this version of it, so I'll box, this is technically the statement of the QES formula. And this is supposed to give you the correct answer for the von Neumann entropy of your CFT subregion to all orders in a 1 over g Newton expansion. So and it's this formula that has done many impressive things that I hope to touch on, like derive the page curve in these 2019 papers. And so I think I'm nearing the end of my time, is that right? And about 5 minutes, okay. And what I want to say is, okay, let me say one thing looking forward, which is that this formula is very good, and it's going to be the workhorse for a lot of what we learn in these lectures going forward. And as I said, it's supposed to give you this answer to extremely high precision, but it's not supposed to be exact. So it's not going to give you the correct answer for S of capital B up to non-perturbative precision in 1 over g. So let me write that here. So there's, let me go over here, and so there's going to be errors. I'm not explaining why we think there are errors. I'll maybe say more about that in days to come. But it will be important eventually that the QES formula has errors. I'll put errors in quotes. I mean that the left and right hand side aren't actually exactly equal. They're just going to be equal up to terms of size like e to the order minus 1 over g Newton. There's some number here. So there's sort of non-perturbative corrections to the formula. So we should not expect it to be accurate to this order. And that's very clear from the derivations of this formula that have come about. I won't say too much about the derivations, but I will say that they involve looking at the gravitational path integral and making some assumptions. And these assumptions involve throwing away terms that are supposed to be very small. but they're very small in this sense. So we usually take G Newton to be small, and there's terms that are non-perturbatively suppressed like this, and when you throw those terms away, you get this formula here. But in principle, those terms should be there, so there are differences in the left and right-hand side of this order. And that's not just a small caveat. It turns out that actually has very deep consequences, which I think we'll get to in the third lecture. It's surprisingly important. So next lecture, what we're going to do, so we're going to turn to understanding in detail what this quantum extremal surface formula tells us, and what's the evidence that it's, in some sense, the most useful tool for understanding bulk reconstruction. Thank you.
Okay. Good. Are there any questions? More? If you...
Yeah, maybe this is a too technical question, but in this extremal surface formula, is it practically easy to map the CFT and ADS states in subregions? If it's whole bulk, I'm giving operators, I know how to map the Kaluza-Klein gravitons and so on, but for subregions, I'm slightly unsure.
Yeah, good. So that's a good question. So I guess the usual algorithm is you have some global CFT state, and then you find the global bulk state, and then you have to. It's not even obvious from the beginning what the bulk region is that is little b. You have to sort of figure that out by trying to find the minimal quantum extremal surface. So that's really the procedure is, and it can be kind of complicated because finding the minimal quantum extremal surface isn't always obvious, but it can lead to insightful physics, like the 2019 page curve papers that computed the page curve in gravity. Really what they did was they computed where the quantum extremal surface was for different bulk states, and they found a phase transition. So for some, at one point at some value of the parameter, the quantum extremal surface formula was here, and then at another value in the parameter, it was there, and that led to very interesting physics. So just finding the position of it was already technically challenging, but very important.
The bulk state itself is very it's circulative, right? I mean, recursive or what? So how do you practically decide it? I mean, do you assume certain states and then extremize to determine B or?
Yeah, good. So practically what happens is, right, you start from your choice of boundary subregion or something like capital B, and then to get started finding little b, you have to know the bulk state. So maybe what you do is you start from vacuum ADS, and then you say act some operator on the boundary that, and then you can use the bulk equations of motion to figure out what the bulk geometry is, say at some later time, and then you can, or as a function of time, and then you can find little b by using that bulk geometry. That makes sense. So that's something people do, right? So you have to first figure out what the bulk geometry is in the bulk state, and then find little b.
But I guess in the second term, I mean, once you determine the bulk geometry, I mean, the quantum states of gravity, like gravitons and so on, can be determined based on that. And but that itself is
Feeds
part
back
of the
into it.
formula that determines B. So do you have to assume something to start with, and check consistency later that it's extremal?
That would be one method. So sometimes what you can do is what you can do is you don't always have to make some strong assumption from the get-go. What you can do is start from some well-understood bulk state and its dual boundary state that you understand, and then you could do something that you understand on both sides of the duality, like act some operator near the ADS boundary, and you know what that does in the CFT, and you know what that does in principle in the bulk. Maybe it's like some quantum quench or something, and dumps in a bunch of matter into the bulk or something, giving you this very time-dependent geometry that you can write down, perhaps, if you can solve the bulk equations. And maybe you have some complicated bulk entanglement pattern, and then it can be challenging to figure out what the minimal quantum extremal surface is, but it's in principle, in this example, a well-specified problem.
Okay. Thank you.
Yeah.
So is so is this region B always smaller than the Rindler subregion?
Good. Great question. Yeah, thank you. So it's the opposite. So this region, little b, is in general bigger than the Rindler wedge. So it's the Rindler wedge is sort of a lower bound on its size. And this is actually very important because this is part of why the quantum extremal surface formula we believe tells us the most about bulk reconstruction. So this little b that shows up in the QES formula is going to be exactly the region that you can reconstruct with capital B. And Rindler reconstruction is just a specific scheme for reconstructing, and it'll say that you can do Rindler reconstruction, say for some smaller region, this like shaded region here. But with Rindler reconstruction, you can't in general reconstruct all the way up to like this part.
I see. So what really distinguishes the two regions?
Good. So they're defined quite differently. So little b here is defined by this formula. That's like the one.
Right. Just from the bulk operator perspective. So what are the operators that cannot be reconstructed using the Rindler?
Yeah.
Rindler
Good.
wedge?
So you can find the Rindler wedge by more generally we call it the causal wedge. By you start from this boundary subregion, and then you have to do this procedure where you find its domain of dependence on the boundary, and then you find in the bulk its causal future and causal past, take their intersection, and in general that might be some, on this time slice, be something like the shaded region. And you can just prove, this is a non-trivial proof, but you can prove it, that the minimal quantum extremal surface will always lie outside of that. So they're both geometric definitions, the causal wedge and the minimal quantum extremal surface. And the minimal quantum extremal surface always gives you a bigger region.
Okay, so then that sounds like from the bulk perspectives, causally non-connected components are somehow connected. Am I?
Let's see. Causally non-connected components.
Do
Good.
Do
Yeah.
interfere or something.
Exactly. Yeah. So this part of the, I should say this. We call this the entanglement wedge. So little b here goes by this name, entanglement wedge. It's kind of a jargony phrase, but I'll say it often. Already here. And yes, the entanglement wedge includes parts that are not obviously causally related to the boundary subregion, and it was surprising to a lot of people. Like some people conjectured, like a decade ago, that the part of the bulk that capital B should know about is just the part that's, say, causally related to capital B. This formula and the theorem we'll see next time prove that's not the case. And perhaps the intuition there is that von Neumann entropy is some measure of information. And so this formula in some sense is saying like the information in capital B is related to the information in little b. And so that's going to underlie the theorem that says capital B knows everything about little b in some precise sense.
So probably it's about the like entanglement property of like causally disconnected pieces.
Something like this, yeah. Yeah.
Thank you.
question in the chat. Sang Jin-shin asked, where is the CFT dependency in the QES formula?
Where's the CFT dependency on the QES formula?
Yeah, this formula.
So, good. Like if you had a different, the way I'm going to interpret the question is if I have one CFT, like n equals 4 super Yang mills, or a different CFT, how does that affect this formula? And so different CFTs will have different bulk duals. Like you'll have different matter in the ADS space. And that will show up in, say, the geometry that you get and the matter entropy configuration. So the different CFTs will have different bulk duals, and that will be very much reflected on the right-hand side.
Are there more questions? Okay, then let's thank Chris again for very nice lecture. So we are having coffee break until 10:50. Okay.
Will you send me your lecture notes? Absolutely, yes. Yeah, okay. I'll write them, and then hopefully by the end of the conference.
Oh, okay, very good. That's good. I hope a lot of people learn so much from this.
Oh yeah.
Great.
Thank you. Good to meet you.
Thanks for me and lecture. Great.
Oh, thank you. Thank you. Yeah, it's very fun. Thank you for the invite.
Yeah, but I was still puzzled with this the last question I asked you. Time in gamma by minimal extremizing, you have to know the states of gravity within.
Yes. Yeah.
So that's why we have to assume.
Right. I think I see the concern. That's very It's very reasonable.
Maybe certain details of this quantum states are ignorable as larger and medium or something. Is that the way people?
That's okay. Yeah, that's certainly true. So like, probably you're more comfortable with perhaps the. Let's talk about the Ryutakinagi formula, where you could say take some like ADS Schwarzschild metric, and then you take your boundary subregion B, and you just have to find the minimal surface. And
So for that case, before extremizing, you know the whole formula. Off-share formula.
Yeah, right. And we can generalize that to like a simple example of the QES formula, where now let's just imagine that the black hole, we're going to allow it to have some entropy S or something, or maybe the black hole, we could say, is entangled with some matter somewhere in the. But yeah, we should have to specify the bulk state first, and then given that bulk state and the bulk geometry, you can find the minimal quantum extremal surface. But if you didn't know the full global state of the bulk, then in principle, you wouldn't be able to.
Don't factor in special examples when you lower dimensional things. What's the states of those?
Yeah, that's a great question. So at first it was kind of conjectured and then thought that it would be in principle too hard to compute anything real. But what really impressed me was in these 2019 papers that I'll mention later on by like Jeff Pennington and then Ahmed and all of them. The meat of those papers really is a computation of the position of the quantum extremal surface in a very non-trivial setup. And so in some sense, it is still like one example. It's not like we can't really do it in general. But but they are doing it in a very non-trivial example. So I would say, so surprisingly, we can compute the positions of these in quite sophisticated setups, but yeah, certainly not in all of them. But yeah, they had to know the full, like, bulk state and the bulk geometry before doing it. So yeah, okay. So Ahmed and them did it in JT, and then, but at the same time, Jeff did it in higher dimensions. But he did make a simplifying assumption of spherical symmetry. So he sort of reduced it to 1+1 dimensional problem. But yeah, so what they did was as you might recall, they had JT gravity coupled to this non-gravitational reservoir, and they imagined that they knew the bulk, like the JT geometry exactly, and so basically some like fixed curve backgrounds, and they had some matter fields that were entangled with fields in the reservoir, and in a way that they knew. So they said it was like entangled, sort of like thermally. I talking would have written down, and then given that geometry and that entanglement structure, they computed the position of the tube sets. Yeah.
Doing things myself.
Yeah, yeah.
Go back and try to get better feeling.
Yeah. Oh yeah.
I have connector, but no, I don't know how to switch it.
Oh, okay. So let me.
Okay, great, thanks. I can do it, I can do it.
All right. And then you don't need a charger? You have enough battery?
Probably, yeah.
Oh, okay, good.
I think so.
All right.
Okay, I just need to somehow switch the camera to the...
Oh, okay, will do.
They will do it, okay.
Oh, okay.
I got it, I got it.
Yeah, I think this is my one.
This is mine. Okay, thanks.
What mic do you use?
Maybe I try this one again. Yeah. But and then I need to switch on the slides. Oh, it's not connected. No. Huh? Not at the moment, no. Just, I can move it, maybe. It's not working. This one. No, or the back, yeah. Okay. Yes.
So while we are waiting, was just told from the local organizers that we'll have a photo session after the second lecture of this morning. So don't fly away right after the lecture. Are we ready?
Yeah.
Okay. So Daniel Baumann will give his third lecture.
Okay, yeah, thanks. Welcome back. Yeah, first of all, I must confess, so once in a while I think it happens that I screw up giving a lecture. And I think yesterday afternoon was one of those days. Okay. Somehow I got too tired and lost concentration. Okay. So if I confused some of you, it's totally my fault, not anything on your part. So, therefore, if there's any questions about yesterday, there's really elementary things that I discussed. Just definition of a wave function, and then we applied it to the simple harmonic oscillator and just calculated the free theory fluctuations. And we just reproduced the standard result 1/2 omega squared for the variance of the simple harmonic oscillator. And you've all seen this calculation in canonical quantization, at least. Many of you maybe have even seen this from this wave function point of view. So there was nothing subtle. Anything that's confusing was really just me being not quite awake, okay? And I even forgot to tell you what the, oh, I'm not, is this on? Yeah. So I even forgot to tell you kind of what the outline was for this part of the course. So what I did yesterday was introducing the wave function of a universe as a concept, and then we started to warm up doing calculations with that wave function in the case of quantum mechanics, and so far only in the free theory. So what I will do today is I will just complete this calculation for the anharmonic oscillator and show you what happens when you include interactions. And there's going to be a bit of a subtlety of computing this boundary term that we had that gives you the on-shell action. And in fact, that subtlety will be universal. That's also the main subtlety of computing the wave function in either in flat space or in de Sitter space or in ADS. Okay. And then we will do a few calculations explicitly, and that's why I'm doing it on the slides, because these formulas become kind of big. We will do explicit calculations for the wave function in flat space, and maybe surprisingly, even in flat space, the wave function is kind of an interesting object. Maybe I can switch to the normal mic because this. Yeah. Okay, maybe this is better. Yeah. Yeah, so even in flat space, we will see that these calculations kind of lead to interesting results. And one feature of these calculations will be that the final answers are considerably simpler than the intermediate steps. So the calculations will start to become more and more complicated, especially then when we go to de Sitter space. Often we can't even do these calculations explicitly. But there's some kind of structure in these answers that suggests that there should be a better way of getting these answers. That we're introducing additional redundancies by integrating over time in the bulk space-time that makes things more complicated than the final answers suggest. And that will motivate us to kind of turn the problem around and try to bootstrap the correlations on these final surfaces directly. Okay? So that's going to be the plan. Are there any questions about things that I said yesterday afternoon? I still have the slides here, so I'm happy to go back and clarify anything that I maybe didn't say very clearly. Okay? Okay, if not, I should also say I will put these slides up on my website. So if you later on, you shouldn't kind of furiously scribble and copy everything down. You can just find them on our website. Okay, so let's go to the case of the anharmonic oscillator. And luckily, Marcos already introduced this yesterday in his lecture. So the anharmonic oscillator is just a simple generalization of the harmonic oscillator with a kind of nonlinear potential term. And so he was writing this down for a quartic potential. I'm going to do it for a cubic, okay? And so for a cubic, of course, you should, in principle, worry that this is unbounded from below and kind of this doesn't have a stable vacuum, okay? In perturbation theory, we'll not see that instability, okay? And so it will not matter for us very much. If you're really concerned, you could redo this entire analysis for phi to the fourth and be safer, even non-perturbatively, okay? But we will just do it for phi cubed because that will be the case that then directly relates to kind of just cubic interactions in the bulk space-time for cosmology or in flat space, yeah? Where we do have a rolling background that's an instability anyway of the vacuum. Okay, so now the logic is exactly the same as we did in the free theory. So we start just deriving the classical equation of motion from this action. And now it has a nonlinear source term on the right-hand side. And because of this nonlinear source, of course, there's not an explicit solution for this equation of motion. But, of course, we can write down a formal solution in terms of a Green's function. Okay? So this solution has two pieces. There's just the homogeneous solution, yeah, which is just a free field solution that we discussed last time, e to the I omega t. And then there's a nonlinear source term that's given by the Green's function of this equation, integrated over the source on the right-hand side. Okay? But this is purely formal, of course, at this point, because the solution appears on both sides. So you somehow have to think of this expression iteratively, yeah, in the sense that you first, at weak coupling, set the coupling to 0, solve the free theory, so you get k of t, or you get the mode functions of the theory. From this, you will get the bulk-to-bulk propagator of that theory, and using that propagator and the lowest order solution, you can then iteratively correct the solution order by order in perturbation theory. So this equation somehow only makes sense kind of order by order in perturbation theory, otherwise it's purely formal because the solution appears on both sides. Okay? So we will see this actually when we expand this expression in powers of the coupling, that how this equation will make sense. But we can write this formal expression. And so there's two types of propagators that then appear. There's the so-called, or what we will later call, the bulk to boundary propagator that tells us just how the free field evolves from some point in the bulk of the space-time to the boundary. That's k of t. And that's just the e to the I omega t of the harmonic oscillator. And then there's a bulk to bulk propagator, yeah, or later we will call it the bulk to bulk propagator. There's no real bulk here because it's quantum mechanics. That's this propagator g. That's just the Green's function of this equation. And so there's one important subtlety here, namely this is almost like the ordinary Feynman propagator in quantum mechanics, yeah, except for this extra piece that I have to subtract. And the reason I have to subtract this extra piece is because this bulk to boundary propagator has the boundary condition that it vanishes when I take any of the two time arguments to the boundary. Okay? So the boundary conditions are that k of t approaches 1 when I get to the boundary, so that the field value at the boundary is little phi. And g of t vanishes at the boundary so that it doesn't get corrected by this extra piece. And we have to correct the Richelieu boundary condition at the boundary. Is that clear? That's very important. That makes a distinction between calculating a scattering process and calculating a wave function. This extra piece in the bulk to bulk propagator that makes it distinct, makes it different from the ordinary time-ordered Feynman propagator. Okay? All right. Now, I won't go through these details, but this is just to say that now deriving the on-shell action is a bit more subtle. Okay? The logic is the same, but there's one little subtlety that arises that I just want to point out to you. And then you can go through the algebra yourself, in my notes. So you start again from the classical action. You integrate the kinetic term by parts to get this total derivative with respect to time. And then something that's proportional to the linearized equation of motion. Okay? So then integrating this total derivative gets you this boundary piece. Okay? But now there's this extra that's linear in the field and then linear and then proportional to the linearized equation of motion. Okay? And so last time we only had this, and since we didn't have this extra inhomogeneous piece, and k was approaching 1 at the boundary, yeah, this was only getting contributions. This became I omega phi squared. Okay? So you might think since g vanishes on the boundary, g will not affect this. Yeah? And so the only subtlety is that, yeah, although g vanishes on the boundary, the time derivative of g does not vanish. And in fact, the time derivative of g is in fact related to the bulk to boundary propagator, like this. Okay? And so inside of here, you will get a contribution from this inhomogeneous source. And so if you're not careful, you will miss this. Yeah? And you will not even notice that you made this error very much, because the only thing that will change in your final answer will be the numerical coefficient of the potential term that you get in the on-shell action. There will be a phi cubed term in the on-shell action at the end of your calculation, and you will just get the number in front of this phi cubed wrong if you miss this term. Okay? But if you keep careful track of it, there will be an interesting cancellation between terms, and you get some right coefficient. Okay? So I will not go through it in detail. How about causality? Okay, causality is implicit in all the fact that I introduced the propagators in the right way. Okay, so then the final on-shell action is this one. I invite you to check this algebra and see this cancellation for yourself. Okay, so it has the piece that's at 0th order in the coupling that we had computed last time, and then it has this naive. This is the thing that people would get if they close their eyes and forget about the boundary contribution of the bulk to bulk propagator derivative, and this is the extra correction term that you get from this. Yeah. Okay. So now, but this is still formal because we, as I said, we only have a formal solution for the classical equation of motion. So now let's actually make this more practical by expanding the classical equation of motion, in powers of the coupling. Yeah. So what we will do is we will take the classical solution, expand it in powers of the coupling, and so we will get functions of time, order by order, in the coupling constant. So, for example, at 0th order, we just drop all the set all the g's to 0, and we just get back the homogeneous solution that we had last time for the harmonic oscillator. Then at 1st order, okay. So at first order in the coupling, well, going back to the, sorry, going back to our, yeah, so going back to our formal solution, at first order, you just calculate this correction term. It's already first order in the coupling. So then I'm just substituting the 0th order solution for my classical mode function into here, just the e to the I omega t. And so that gives me the first order correction to this solution. Or just this? Okay. Yep. Okay, so here I just iteratively solved the equation of motion at 0th order and then at first order. And you can go through and do these integrals. And so then you just plug that back into the on-shell action, and you can just expand order by order the argument of this exponential in the coupling, okay? And you will get interesting coefficients like 1/9, 1/72, and so on, okay? So in fact, Austin and I, if you get the boundary term correction wrong, if the subtlety that I just kind of highlighted, if you get that wrong, you will not get the 72. And just getting the 1/72, and you can check it against Bender and Wu or someone who did this calculations kind of canonically. And so you just have to hit these numbers here, and so that requires a bit of care in these calculations, okay? And I know this because I never got these numbers right first, and then I knew that I was screwing something up, and I get back and fix this, okay? Okay, but then given the weight function as such an expansion here, you can compute, you know, phi cubed and phi fourth and everything you want, or kind of the energy levels like Marcos was describing yesterday, okay? Okay, any questions about this? Sorry? Sorry, that what is, well, it comes from literally, yeah, it comes from the bulk-to-bulk propagator terms. I'm not sure. Let me think about it, I don't, yeah. Okay, so I think actually this anharmonic oscillator is a useful toy, a useful warm-up, to understand first, because like really the wave function calculation for field theory is exactly the same with a couple extra indices in Fourier space and so on. But the essential elements of like computing the classical solution carefully with kind of the right boundary contributions and so on already appear at the level of just quantum mechanics. Okay, so you somehow need to disentangle what's subtle, what's just kind of an extra nuisance of having Fourier labels and delta functions and so on, and what's kind of physical subtlety about evaluating things at the boundary in time. Okay, so that's why it's relatively easy now to go to field theory. Okay, so we're going to study a model that's exactly the same as this, just in space-time. So we have a kinetic term for the field, we will have a mass term for the field, and a cubic coupling. And so then the analysis we write out explicitly in the lecture notes, but I'm not going to do it. It's exactly the same as what I just did, just a little bit more messy. So in the interest of time, I will jump directly to Feynman rules for these wave function coefficients, which are kind of intuitive. Okay. So if we have a diagram like this, like for example a 4-point with a single exchange, the rule is you attach a bulk to boundary propagator for every external line. Okay. And because this is a massive field in a curved spacetime, this bulk to boundary propagator may be a more complicated function now. Of course, it's not just e to the I omega t or e to the I kt. It could be a Hankel function, for example. It typically is a Hankel function in the Sitter space. So the functions become more complicated, and that's why we'll have a harder time evaluating time integrals that appear in these expressions. Similarly, for every internal line, you have a bulk-to-bulk propagator, with this, which is just the ordinary Feynman propagator minus a correction piece that gives it the right boundary condition. And then importantly, and this is what makes it really different from calculating a scattering amplitude, is that because energy is not conserved, we have a boundary in space, even in flat space. When we calculate the flat space wave function, we introduce this boundary condition at t equals 0, and then integrate from minus infinity to t equals 0. That breaks time translations, so energy therefore is not conserved in the system. And so we need to integrate over every time vertex in quantum mechanics, and those integrals will be non-trivial. While for the S matrix, we integrate from minus infinity to plus infinity, energy is conserved at every vertex, and therefore these time integrals always just give you energy conserving delta functions, and you just do them implicitly. They're not even mentioned in the final Feynman rules anymore, okay? So the key difference between calculating wave function coefficients and S matrix elements is the fact that you have to face the fact that energy is not conserved and need to integrate over time, okay? And we will see that in cosmology, these integrals typically cannot be done. And so then we have to ask what we do in such a situation, right? And so importantly also, if there's an expanding space-time, then we have an extra measure factor, 3 powers of the scale factor in these time integrals. Okay? And so that's where the cosmology dependence will enter here, and it will enter in the functional dependence of these propagators. So those are the 3 elements. You know, you have bulk to boundary propagators, bulk to bulk, and integrations over time. Okay? Any questions here? Okay? So now we can just go and compute a few things. And so you might ask, why am I going to do this? Yeah. So why compute things? So the reason is I want to just show you a few past the light gun, I don't know. Maybe you can ask me later. Yeah, so the reason I want to go through a few of these calculations is just, first of all, to show you a little bit of the mechanics, but that's not the essential reason. And, but also just because we're going to develop a bit of theoretical data, in a sense, that we're just going to calculate a few processes and look at the answers. So rather than the individual steps of the calculations aren't so important, except to impress on you that they kind of become complicated eventually, rather quickly. But the fact that the final answers have kind of structures, singularities that we should investigate a bit more closely. And so that's going to be the point of showing you a few explicit results, okay? And so in fact, tomorrow we will turn the whole problem around and try to reconstruct these answers from an alternative point of view, because there is this hidden simplicity somehow that strikes us when we look at the answers, okay? Even flat space. So let me actually just start with the flat space wave function, which is just a slight embellishment of the harmonic oscillator in quantum mechanics. Okay? So even flat space, this is an interesting object because we're integrating over only the half space up to a fixed boundary in space-time. We're going to look at this toy model, which is the same as before, except I've set the mass to 0. Okay? Just for simplicity, I'm going to do a massless field where the propagators in flat space are just the usual harmonic oscillator plane wave solutions. Sorry, I shouldn't touch this. Okay, thanks. Yeah, this is the second time I'm using this in my life somehow, but yeah. Okay, so we will study this massless field with a cubic interaction, and we're going to evaluate this as a fixed moment in time, which without loss of generality, I can always set the time equals to 0. Okay? And then we're going to integrate from minus infinity in the past to 0 in the future. The propagators are exactly the same as for the harmonic oscillator. I'm just replacing the frequency is omega with the magnitude of the wave number k, or if the wave vector, which is the wave number k, okay? Otherwise, these are exactly the same propagators that I just showed you in quantum mechanics. And so now we will just compute the simplest tree-level correlators in this theory, okay? So at 3 points, we have a 3-point vertex in the bulk, and we need to integrate this vertex over time. It's flat space, there's no scale factor, so it's just literally just a simple integration over time. And then there's 3 factors of the bulk to boundary propagator, 1 for each line attached to the boundary, okay? And then each bulk to boundary propagator is just an e to the I kt with k1, k2, k3 running through the 3 different lines, okay? And now this is, of course, is a simple integral because it's just e to the I sum of all the k's times t, okay? Because of our I epsilon prescription at early times, this only receives a contribution from the boundary at t equals 0. And at that place, it will just turn into a 1 over the sum of all the k's times the coupling constant g. Okay? So it's a very simple answer. One thing to notice from this answer already is that it has a singularity. It diverges when the sum of all the energies of the lines add up to 0. Which is, for a scattering amplitude, we would get a delta function in the sum of all the energies. And for scattering amplitudes, there can be ingoing and outgoing particles, so the energies can be positive and negative. In cosmology, we have only positive energies. There's no outgoing particles, only ingoing. Okay? So this is not a singularity that we can probe in physical configuration space, because all the energies have to be positive, so they can't cancel. Okay? But is viewed as a kind of a function in complex momentum space. The singularity is there, and as we will see, the singularity will actually determine the structure of the answer, often very strongly. And so we will later have much more to say about these singularities. Okay. All right. Now this calculation, of course, is easily generalized to n points, because then you just get n of these lines. You get an e to the I kt for all of the lines. They just combine, the sum combines. So the answer really just depends on the total energy entering this vertex from the boundary. Okay? So you get the same pole with just the sum of all the energies for all of the lines. And that's just the fact that the product of e to the I kts will sum in the exponents. Okay? It's a special feature of flat space. This would not hold in a general space-time. Okay? So there's a few things that are really special to flat space, yeah, and this is one of them. Okay, so this hopefully was very elementary. So slightly more non-trivial is calculating this exchange. So we have cubic interactions, so we can have a diagram like this, where there's two vertices in the bulk, cubic vertices, one bulk-to-bulk propagator running through them, with an intermediate momentum or energy ki, and then 4 energies labeling the external lines. Okay? So applying the Feynman rules, you just get this integral. 2 integrations over time, integral over t prime, e to the I, and here I'm using the notation that k12 is just the sum of k1 plus k2. That's the sum of the 2 lines entering this vertex. k34 is the sum of the energies entering this vertex. Okay? And then there's a bulk-to-bulk propagator running between the 2 vertices. 2 powers of the coupling with a factor of I that gives me an I squared equals minus. Okay? So that's the integral that I have to compute. Okay? So if you go back and remember that this bulk-to-bulk propagator in fact has 3 pieces. 2 pieces that are just the time-ordered Feynman propagator, and then 1 piece that's this correction because we have this boundary condition that the propagator has to vanish on the boundary. So there's 3 of these pieces. Each of these pieces you can integrate relatively simply, and it will give you these 3 different colored terms. Okay? And then these terms actually combine into a rather simple, and I will show you in a moment, kind of suggestive answer. Yeah? So these intermediate steps are more complicated. This is a baby version of this general lesson that the intermediate steps of the calculation will be more complicated than the final answer. So the final answer is just this. Okay? And so I claim this is remarkably simple, and it has interesting singularities, if you look at it. So now there are 3 poles. There's 1 pole here, which is the sum of all the external energies. So I call this a total energy singularity. That's exactly the same as what we had for the contact interaction before. And in fact, this will be a universal feature. Every correlator will have a singularity at the point where the sum of all the energies of the external legs add up to 0. Okay? And then the residue of that singularity will be extremely interesting. I will show you later. Okay, so that's 1 singularity. Then there's a second singularity at k1 plus k2 plus ki, which is precisely the energy entering the left vertex. So remember, the left vertex has 2 lines, k1 and k2, and then it has an intermediate line ki. This is the sum of all the energies of those 3 lines meeting at the vertex on the left. And then similarly, there's a sum of the energies entering the right vertex. Okay? So there's 3 poles which all correspond to energy conservation. In flat space, these would all be delta functions. Yeah? So the total energy delta function, energy conservation, and then for each of the vertices also energy is locally conserved for every part of the subdiagram. Okay? So you would delta functions in flats in for the S matrix. Here you get poles. Okay? It should not be dependent on what? On Ki? Sorry, it does have Ki. So remember, Ki is this. So each of the line, in fact, has a 3 momentum attached to it. And Ki is the magnitude of the 2, 3, because momentum is still conserved, just energy is not. Very important. Okay, let me go back and say this. So each of these lines has a 3 momentum K vector. Okay? And then these Ks without a vector symbol are the magnitudes of those vectors. Okay? So momentum is still conserved because we have translation invariance. That's not broken. Translations in space. And so K1 vector plus K2 vector equals Ki vector. And then it's just the magnitude of the Ki vector that's not the same as K1 energy, K2 energy. Yeah? Is that clear? Super important. Yeah? So we have broken translations in time, but translations in space are always, even the most drastic cosmology case, are never broken. We live in an isotropic universe. And therefore, 3 momentum is still a conserved quantity at every one of these vertices. Okay? But energy is not, and so you actually separate. We don't have 4 momenta. So for scattering amplitudes, once you specify the 3 momenta at every leg, you also know by the dispersion relation what all the energies are. And momentum conservation kind of linked by Lorentz invariance. Okay? Here we don't have Lorentz symmetry anymore, and so you separate energies and momenta because you're splitting time and space. Okay? Okay? But as I said, I will have more to say. I will have a whole section just on singularities. Because later those singularities will be a very important element of trying to bootstrap these answers directly. Basically, these answers will have to have the right singularities in order to be self-consistent. Okay. Any questions about this? 2 pages before? Yeah. No, in phi cubed you wouldn't. No. This, if I had phi to the n theory, of course, I would have a corresponding endpoint wave function coefficient. Yeah, of course. So here, just for these 2 lines, I've snuck in an extra coupling in the bulk, for sure. Yeah. At loop level, you could, of course, have. Yeah. Sorry, the boundary condition of what? Yeah. Uh-huh. Yes. Shall I repeat what they are? Oh, the reason is just that when I write for the harmonic oscillator, I was splitting the solution into 2 pieces. There's a linear evolution that's just phi times k of t. And I want the final value of the field is defined to be phi. So if I'm defining k to have boundary condition 1 at the boundary, then whatever I'm adding as an inhomogeneous correction to this should not contribute at the boundary. Otherwise, it will not give me the right. Yes. And at the same time, you are specifying the boundary value of the field. Yes. But I'm also giving a wave, then I'm calculating a wave function. So I'm not specifying it, I'm just saying it is what it is. There's some general profile that is what it is, and the wave function will give me the probability distribution for that arbitrary field profile. I'm just giving it a name. I'm not specifying it. I'm just calling it phi of x. Yeah. I just gave it a name. I didn't specify anything in that sense. But then whatever it is, the solution has to reflect the name that I gave it. Yeah. Thanks. Any other question? Okay. So you could keep going now. For example, as an exercise, you could calculate the 5-point function where you have 3 vertices in the bulk. It's a 3-dimensional integral. Now this becomes kind of nasty. You have 3 nested integrals, and you have to try and do it. Fortunately, actually, in flat space, there's a really powerful recursion relation that allows you to build up any tree-level diagram from basically 3 points with shifted energies. In the notes, I derived this recursion for you. Here, I'm just suggestively telling you that you can cut all of these diagrams at the individual lines, and the sum over all, there's a rule for summing over all possible cuts, giving you the more complicated diagram in terms of all the lower point. Yeah, so you can recursively, once you know the answer for 3 points, you're essentially done. You can glue together in a well-defined way 3-point answers to get even the 4-point that I just showed you, you could actually get from the 3-point answer that we had before, and then 5 points and so on can be done in the same way. So for flat space, there's just enough, there's additional symmetry somehow that we don't have in cosmology that allows you to kind of recursively generate complex things from simple things. Okay. I wish we had something like this actually in the sitter. We don't. Yeah. Okay, so this is just what I wanted to show you about flat space. Already at that level, kind of it's kind of instructive to do a few of these calculations and look at the answers. And so let me now just show you a little, with a few examples, what the extra challenges that we get when we go to the sitter space. Okay. Yeah. This, yeah.
So these Ks are not taken to the boundary, like.
They are taken to the boundary. These KIs, you mean the ones that I'm cutting? Yeah. They are taken to the boundary. Yes. Yeah. So what this means is that, yeah. Let me come to me afterwards. I show you more detail. This might be more confusing to others than helpful. Okay. I can show you the rules precisely. Okay. So let me now upgrade to the sitter space. And the logic is exactly the same. The calculations, the Feynman rules are exactly the same. The functions will just be more complicated. So instead of these e to the I kt things that we can simply integrate because all of the integrals are doable, we will get, in general, Hankel functions. Okay? And integrals of Hankel functions are just nasty. Okay? That's just a fact of life. So the reason that's the case is, imagine you have a massive scalar in the sitter space. For the moment, let's just be a free field, yeah? Just to get its linearized equation of motion. The canonically normalized field, which I used to call U, which is just the original field rescaled by the scale factor, has the following action. Because it's canonically normalized, its kinetic term and its gradient term are exactly that of flat space. Okay? So the only place where the expansion of the universe enters is in this time-dependent mass term. And in fact, we have seen this before because we did calculations for massless fields in the sitter space, where this term was absent, and we had a +2 over eta squared as the time-dependent mass term for the field. Okay? The only thing I did here is now I added a mass term for fun. Okay? And in fact, not just for fun, because we can choose, you notice that there's one special value of the mass, namely when the mass squared is equal twice the Hubble scale, where this extra time-dependent mass term actually vanishes. That special value is called conformally coupled scalar. And we will do a lot of explicit calculations with that value of conformal coupling, where the special feature that happens here is that this mass term now vanishes for that value, so that the canonically normalized field, not the field phi, that's important, but the field U, is literally just flat space, the flat space wave mode function. And then the only place where the expansion of the universe comes in is in the translation from U to phi. Okay, so then the calculation is as close to flat space as we can possibly get. There's a little bit of de Sitter in it, because there's extra factors of the scale factor in various places. But the mode functions have this e to the I kt, because the U mode functions don't have a time-dependent mass in it. Okay? Because in general, the equation of motion would be this one. It would have this non-trivial mass contribution. And the general solution to this, with the right boundary condition at early times, so that is Sponge-Davis, is the second Hankel function of the second kind of this type, yeah? With an order of the Hankel function that's just given by this index nu, which depends on the mass of the field. Okay? And so for arbitrary masses, this is just what you have to deal with. This is a second Hankel function of the second kind, and this will pop up all over the place. Yeah, in all of the bulk to boundary factors, all of the bulk to bulk factors, this would show up. And so there's just no chance in hell to do these integrals. But as I said, there's a special value where we can do some analytic calculations. Yeah, as I said, for conformally coupled, it just reduces to a canonically normalized field in flat space. It has the usual mode function, okay? And so we will, when we want to do explicit calculations in the bulk, we will often do this special case because we can, okay? And then actually in the cosmological bootstrap, we will see that these results that we get for the conformally coupled scalar, which are the ones that are most easily bootstrapped, can then be upgraded to massless fields or any mass fields by so-called weight-raising, weight-changing operators. So those are things that are important in conformal field theory, and they also will play an important role in our de Sitter constructions. Okay. So this is not just of academic value. This will also be a seed function from which more complex correlations can be built by some differential operation. We will see this tomorrow. Okay. Okay, but let's try and do a few of these calculations just for conformal coupled. Okay. So in general, the bulk to boundary propagator will be this one if the mode function of my field is called fk eta. Yeah, so that's just the function u of k that I showed you divided by the scale factor. That's the mode function for the original field phi. I called it f. Yeah, f for field. Okay. So of course, these mode functions satisfy the right equation of motion in order to be Green's functions or propagators. And then I just have to divide out kind of the value of this function at the boundary in order to normalize correctly the boundary condition at late times. So k has to approach 1, g has to approach 0 at the boundary. And so you can check that this abstract expression here satisfies this boundary condition. As I said, in general, all of these f's here are Hankel functions, and this will be complicated. But we can do calculations for conformally coupled. So, for example, let's go back to 3 points. Abstractly written, this becomes a function like this. We have to integrate over 4 bulk to boundary factors, which each of them becomes just this function f. Okay? And so this is a product of 3 Hankel functions, which can actually be expressed as an apple f4. But who knows what apple f4 is, okay? So it's not very illuminating to actually just, there's an integral representation of apple f4, and mathematicians have learned some things about it, so, but it's not like, it's not great state of affairs, and it will get worse, okay? For conformally coupled, yeah, so you get an integral that is almost as simple as in flat space, except for this factor of time. Yeah, notice in flat space we just had an integral over time of this e to the I kt, e to the I k1 plus k2 plus k3 eta. Here, because there's additional measure factors both in the wave function, both in the mode function and in the measure of the integral, there's a remaining functional dependence on time that appears here. That's the only difference. Okay, I can still do the integral, and I will get a log of here. Capital K is just the sum of the energies. Yeah. Okay. This factor of I inside of the log is subtle and comes from our I epsilon. That's actually quite subtle to get this right. You should check the notes. Okay. And then if you wanted to go from a wave function coefficient to a correlator, you have to take the real part, carefully taking the real part of this log with complex arguments and so on actually makes this log cancel. And so this would be the answer for the actual correlation function on the boundary rather than just the wave function coefficient. Okay. So it gets already a little bit more complicated, but here's still totally analytic and manifest for conformally coupled scalars. Why are they causal? Somebody is really worried about causality, but I'm using kind of just ordinary Feynman rules of in solving the equation of motion in the bulk spacetime. So they're causal just because everything is set up from a local Lagrangian in bulk perturbation theory. So I don't see why it could be acausal. Okay, if we now wanted to do 4 points, yeah, imagine you do the 4-point wave function coefficient for a conformally coupled scalar, then this extra dependence of the measure on time actually cancels precisely, just for this particular value of 4 points, because a 4-point coupling actually maintains the conformal symmetry of the free theory. So the conformally coupled scalar has a Weyl symmetry that relates it to flat space, okay? And just for phi to the 4th, that symmetry is not broken by the interaction, okay? And that's why we should expect to get exactly the same structure as we got for flat space, except for maybe a rescaling, a constant rescaling up front here by normalization factors, okay? And that's indeed what you find, because this extra time dependence cancels completely, and so what you're left with is just a pole of the sum of all the energies, which is precisely the structure that I advertised you get always in flat space contact, okay? So this is a special case where conformally coupled and flat space are the same. All right? Any questions about these calculations? Yeah. Yeah. Yes. Yeah. 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 Yeah, so this is actually a very interesting question. So there's a few things here that are, when we write down a Lagrangian and do bulk perturbation theory, are completely manifest, like locality and causality and those type of things. When we try to then reconstruct these things from the boundary and forget about the bulk calculation completely, it's actually a good question what all of these things correspond to. For example, also unitary evolution in the bulk spacetime is just manifest because we have introduced kind of a local Lagrangian with a Hermitian, Hamiltonian, and so on. Yeah? But if you want to kind of strip away all of this kind of time integration in the bulk and just ask how can we reconstruct the final answer without any reference to the bulk spacetime, we need to have some kind of alternative principles that tell us what locality means and what causality means and what unitarity means and so on. And so this is going to be the whole point of the next part of these lectures, to actually kind of, we don't know all the answers, I should say, but to give you some first understanding of, so locality is somehow related to these poles actually. So these total energy poles at would-be energy conservation for every point in the bulk is a reflection of locality in the bulk spacetime. So from the point of view of the boundary, you just have to specify the right singularities in order to be local. For example, if any of those singularities had been higher order in flat space, that would be non-local. So in flat space, actually, these have to be all simple poles and so forth. There will be certain rules for what type of singularities are admissible in a local theory and what type of singularities are not. But from the point of view of the boundary, all you see is momenta and energies living on the boundary in space. There's no time anymore. And you have to reconstruct consistent time evolution from kind of analytic properties of these correlation functions. And so that's going to be the whole point of kind of trying to reformulate how to do these calculations. Or basically how to get an answer without calculating, because we don't want to calculate these things. Okay? All right, so let me just show you one more example, which is this 4.3 exchange, because that's going to be a prime example that we also then later going to try and bootstrap. So in a cubic theory, we have, again, these vertices here. We have a bulk-to-bulk exchange. Applying the Feynman rules, you get the first line here. And so it's almost like what we had in flat space, again, with these extra 1/time factors in the measure of the time integration. Okay? So now one trick you can do is, if you're worried about doing the 1/time additional integration, what you can do is you can introduce an auxiliary integral. For example, here this integral from k12 to infinity of dx of e to the I x eta, and remove the 1/eta. Yeah? That integration, of course, will generate for you from the e to the I x eta the 1/eta. It's just an integral representation of 1/eta. Yeah? And so the reason I'm doing this is because when you do this, you have these red and blue integrations, but the remaining part, which is green, is just our flat space integral. So we can substitute for green, everything in green, just the answer that we got in flat space, which was this simple answer which has just 3 poles, 1/the total energy, 1/the energy of the left vertex, 1/the energy of the right vertex. And so we can substitute, this is what this integrand is. So we have this 2-dimensional integral representation of the conformally coupled scalar in de Sitter in terms of the flat space. So there's a way of kind of integrating the flat space answer to get the de Sitter answer in this specific case. Just because they were so simply related by just these polynomial rescalings by a factor of time. So it actually turns out that you can do this integral. Actually, let me tell you a little story because I found it amazing. So I now spend a lot of my time in Taiwan, and at NTU, the students are amazing. Undergrad students are amazing. Okay, so this integral for half a year, I didn't know exactly how to do. So Nima and Juan Maldacena, they somehow wrote down this integral as their answer, and it seemed to like they suggest this was obvious. I think it's super subtle how to do this integral. Okay, I still think it's subtle. So it turns out you can do this integral. You will get a log and a dilog. Okay, if you're careful about kind of choosing the right branches of integration and all that kind of stuff. Anyway, so I was giving a presentation to these undergrad students, and one of the students was doing it in real time. So literally in 10 minutes, he just got this with Mathematica. And so I'm still, yeah, it's a crazy kid. Yeah. Sorry? Yeah, sorry. Yeah, sometimes I keep the eta star explicit. For example, here we actually see that there's this divergence when I set eta star to 0. And so that's why it was somehow important for me to not set it to 0, but keep this IR regulator of eta star. So okay, I'm switching back and forth between keeping it finite and small and sending it to 0 at places where it doesn't lead to divergences. And so here there's a place where it actually would lead to a divergence when I send it to 0, and I have to be careful. Okay. Okay. So it's already interesting to notice that there's logs and dilogs appearing, because later, maybe if I have time tomorrow, I will tell you about a new paper that we're just finishing, which is trying to answer the question, what type of functions can appear that are consistent with causal and local and just consistent cosmological evolution in the bulk space-time. And we're going to partially answer that question in a new paper. And this is a specific instance where for conformally coupled scalars in de Sitter space, there's a kind of polylogarithmic structure. If you calculated a 3-point function, you would get a trilog. So there's kind of integrations of logs somehow that appears in these answers. And we have now a better understanding where these come from and how those generalize to FRW space-times, not just de Sitter and so on. So if I do have time, I might tell you about this tomorrow. Okay. But okay, so far this was still pretty limited because like we only got like, we went epsilon away from flat space by kind of going to the special value of the mass where the field was conformally coupled. And so therefore its mode functions were as close to flat space as they could possibly be. And we didn't have to deal with any of the Hankel function behavior. So the next simplest case you could imagine is still leaving the external fields conformally coupled scalars, but exchanging a generic massive field, which means the bulk to boundary propagators will be simple, e to the ik eta, but the bulk to bulk propagator will now be a complicated product of Hankel functions. And even that simple case cannot be done, okay? And so that was the state of affair as of maybe like 3 years ago, where this simple process, which is kind of the analog of 2-to-2 scattering at tree level, which for the S matrix is something that is one of the first things you do in your textbooks courses. Even that thing we know it just could not compute in cosmology. So that's a bit of a limitation, okay? So I will describe for you therefore like an alternative, a different approach and try to tackle this integral and variations of this type of problem. All right? Any questions? My phone is out of battery, so I don't know what time it is, but how much time do we have? 30? Oh, great. Okay, because I actually wanted to switch to the next lecture, basically, so I have to switch slides. But I can take questions on this part now, if there is. Is there anything?
Is there a way to generalize those recursion relations for any spin?
Sorry?
Is there
To any spin?
Yeah,
On the outside or on the inside? Or whatever?
whatever.
Yes. So actually, there's a relatively, and I mentioned this briefly already, that there's this so-called concept of weight changing operators in conformal field theory. And part of the weight changing is actually also changing the spin of the field. So there's kind of spin raising, spin lowering operators. These are differential operators that are actually naturally defined in embedding space. So embedding space is this kind of two-dimension higher space in conformal field theory, and where the conformal symmetries become kind of linearized and become kind of Lorentz symmetries on a null cone. And so in that embedding space, there's a whole systematic formalism of changing the weight of the field and also changing the spin. And those weight or spin changing operators can easily be Fourier transformed, because the whole challenge in cosmology is that we don't have position space, or we're not interested so much in position space. Otherwise, as we will see, actually the boundary is a conformal field theory. And so you might think, why can't we just import all of the technology of conformal field theory and so on? Part of the problem is that most of the conformal literature, most of the powerful results are formulated in position space, and we need them in momentum space. And it turns out that the Fourier transforms are non-trivial. And so it turns out actually to be easier not to try and Fourier transform. These Fourier transforms have various divergences and need to be regulated, and it's all a mess. So what one does instead is one tries to re-tackle the problem directly in three-dimensional momentum or Fourier space. And And so we will actually see this in the next part of the lecture, but just to tell you that these spin raising and weight changing operators are kind of relatively easily Fourier transformed. So you actually know them in both position space, embedding space, and momentum space, and then you can use them. Okay, and they're very powerful, and they allow you to start with just some simple scalar seed function, made maybe just out of conformally coupled scalars, for which we can do these integrals, and then just change the answer by acting on it with a differential operator, and getting answers for all kinds of different things, different spins, different masses, and so on. But there's some underlying seed, some underlying simple structure that determines what everything else looks like. Okay? So there will be complicated answers that people have calculated laboriously, explicitly, that we now understand that all the complication is just coming from the fact that there's differential operators that take a simple answer and make it complicated. Okay? But there's a nugget, like an atom of correlation that underlies all of this.
A comment or maybe question in
Yeah.
the chat. He said needs to specify the initial state. I'm not sure it's a question or comment, but maybe you can talk about some.
The initial state?
Yeah, initial states.
Yes. Well, remember the initial state I described yesterday. So in this wave function approach, the initial state is defined as the boundary condition of the classical solution at early times. So in order to define this path integral over all bulk field configuration, we need to specify two conditions on the field, namely what the field is at late times, where it has some prescribed boundary value, little phi of x, and what it is at early times. And at early times, it just should approach e to the I omega t or e to the I k eta, just a flat space mode function with purely positive frequency. So then when I was writing down bulk to boundary propagators and bulk to bulk propagators, notice that they were always coming with the right positive frequency mode functions. So that's where the initial state is hiding. It's hidden inside the fact that all the mode functions that I'm choosing to define my propagators have the right initial boundary condition of purely positive frequency. So I hope that was the question. Okay? Yep.
Maybe this you trying to explain the this inflation, so you maybe talk about the scalar, or but is it possible to study this fermion in the de Sitter space and doing some similar thing?
Sorry, fermions?
Yes.
Yes. Yeah, it's an interesting question. Hasn't been done really. I know that Yutin Huang, my colleague at NTU, is doing it with a student, and other people are looking into it. Because, for example, one interesting question is if you could write down correlators for massless gravitinos, yeah, spin 3/2, because there's an interesting interplay, with SUSY breaking. That so in flat space you can prove, for example, that the interactions, and this is in fact something we were going to get to in a few slides. So massless particles in flat space have highly constrained interactions. So, for example, a spin 2 particle, the interactions are under certain conditions, which I will describe maybe. Interactions are uniquely long-range interactions are those of GR. This is a beautiful, beautiful, beautiful thing that one can prove. Same for a spin 1 particle, you kind of uniquely led to Maxwell's equations. And spin 3/2, must be supergravity in flat space. But we know that if you try to do it in the de Sitter space, you need to somehow see the effects of SUSY breaking of the de Sitter vacuum energy. And so it would be very nice to see this at the level of these correlators somehow, how these theorems must break down because of de Sitter curvature. And so that just has not been done. It was always something I would like to do eventually. It's just but actually these fermions, they can be treated with these spin and changing operators that I just described. They're fermionic versions of this, and you can do these type of things. Okay. Apparently, there's actually subtleties about defining the initial state for the fermions. That's what I'm being told, but Yutin maybe will write a paper, and then we will know. Yeah. Okay. Any questions about this last part? Okay. So this was extremely explicit, just to impress on you that, even for simple cases, this becomes complicated. If we try to do it now, more complicated cases would just become undoable pretty quickly. Okay. And so we're therefore motivated to try and kind of try something else. Okay. And so this something else is going to be what we call the cosmological bootstrap. So what I will do today is I will just describe the basic philosophy, I think, and then next time we will see how far we get in both describing all the principles that are at play and giving a few examples of applying this bootstrap method to cases that we can't compute in the ordinary bulk perturbation theory. Okay, so then let me first of all, just to remind you, so what we discussed in the very first lecture is that if inflation is correct, well, first of all, we discussed there are correlations that we measure at late times. On the weak assumptions, we can trace them back in time to some initial surface, which we call reheating or the hot Big Bang. Okay? That's kind of relatively model independent. Okay? That's our cosmological standard model. What is model dependent is what happened before. If inflation is correct, then what happened before is that there was a phase of quasi-de Sitter expansion. And this initial surface of the hot Big Bang will be attached to the final surface of this de Sitter spacetime. So de Sitter space has a final surface at eta equals 0. At a finite but small eta, this surface will get deformed and will be attached to the hot Big Bang surface. So the pure de Sitter will end, and the hot Big Bang will be generated. And so that's this gray surface that I'm drawing here. Yeah. Okay. So the question now is, and we're observing correlations only on this gray surface. There's just no way, even conceptually, to observe anything that happens directly inside. Okay. It's just not possible. Okay, we don't have observers during inflation. We never observe the inflationary dynamics directly. All we have access to are these static correlations on this spatial slice. And somehow our challenge is to reconstruct bulk dynamics from those static observables. Okay. So the question is, can we do this by only focusing on observables? So basically, these time integrations are stories that we made up. Yeah, they're not directly observable. They're just like our model for what might have happened. But maybe you can kind of bootstrap the boundary directly and get rid of kind of this model and kind of replace the model with some extra principles that live purely in the space of physical observables. Okay, so that's the general bootstrap philosophy, and that's also what we want to apply here. So the conceptual advantage of this is that we're going to focus directly on things that we can see, densities on this final surface. Okay, and we don't make any reference explicitly to unobservable things happening in the bulk of the spacetime. Although, of course, we must reconstruct somehow the model-dependent things from alternative principles. Okay? And then the practical advantage will be that in many cases, this simplifies calculations. So if your goal in life is to calculate, this will help avoiding some grief in these calculations. Okay? But I think it goes beyond just being able to calculate more and more things. It's actually a kind of an alternative perspective that changes also your thinking about how to describe the physics of this era. So now, of course, this bootstrap perspective has been very influential in many different areas. Two important areas is, scattering amplitudes in flat space, and another one is conformal field theory. The one that we're going to take most inspiration from at this point is actually S-matrix bootstrap. Okay, so in that case, there has been enormous progress by focusing just on observables living at asymptotic infinity. So there's a set of states, on-shell states initially, and there's of course the S-matrix that describes the probability for that state to transfer to some final state at the infinite future. Okay, and Lagrangian perturbation theory is the way of calculating in order by order in perturbation theory the S-matrix, how you go from some initial state to a final state via an infinite series of perturbative processes. And what I will sketch later is that this Feynman diagram expansion is very inefficient. Especially in gauge theories, you have to introduce redundant degrees of freedom. There's an exponential proliferation of Feynman diagrams. It's very much related to what Marcos was describing in his lectures. There's this n factorial growth of things in perturbation theory that's related to the fact that the Feynman diagram expansion is blowing up in your face. Okay, so one way of rectifying this, and it basically arises because we're introducing all these virtual things, additional longitudinal polarization modes of that are constrained by water densities and so on in the gauge sector that we never observe. Yeah, nobody has ever seen these virtual particles. All we ever see is clicks in a detector from on-shell external particles. So there's a whole technology of trying to describe things in just an on-shell manner of just focusing on the observables. Okay, and in that case also it dramatically simplifies calculations, much more than what I've shown you so far. Yeah, so there's a famous result where explicit calculations that ran over many pages So for example, the scattering of 5 gluons. Yeah? 4 gluons you can maybe do as an exercise in your homeworks. 5 gluons is totally impossible. There's 25 Feynman diagrams. The Feynman rules are complicated. It's 25 pages of terms. And then there was a heroic calculation by Park and Taylor that showed that these 25 pages, in fact, when you carefully sum them up, give you a simple one-line answer, the Park-Taylor formula. Okay? Or for 4 gravitons, even worse, I think it's hundreds of diagrams, similar number of pages, and DeWitt calculated it and got a very simple expression that I can kind of draw in the palm of my hand. Okay? So there was clearly something where Feynman diagrams were just not the right way to go about getting a one-line answer from like 100 pages of algebra. Okay? And so it simplifies these calculations enormously. And then by having simple answers, you can stare at them. You can look at the simple answers and look for structures. And people found amazing new symmetries, even in old theories like GR or Young-Mills. Yeah? They found new hidden symmetries, hidden Youngian, conformal, dual conformal, all kind of things with, that were only possible to realize because you had a more efficient way of getting on-shell amplitudes directly and getting rid of Feynman diagrams. Okay? And so we will try to replicate a very modest version of that success story in cosmology. Yeah? And I will show you how far we have gotten. Okay, that's what I just said. And so the goal will ultimately be to get to a level that we parallel this amazing understanding that we have gotten in the last couple of decades of flat space amplitudes. But just to warn you, I guess my estimate is that we're kind of 20 years behind the S matrix in cosmology. Okay. So for the S matrix, for example, a 2-to-2 tree-level exchange was solved, ages ago. We just solved it 3 years ago, and so there's still a lot of work to be done to get to the level of understanding that we have for the S matrix for cosmology, which is of course great for young people. I mean, you still have 20 years in you, and I might have, if I stay healthy, have 20 years of catching up with the S matrix bootstrap program. Yeah? All right, so this is going to be my outline. And I will need some warnings about time, please. Yeah? 15? Okay. So I will just have time to describe a little bit more this philosophy today, and then we will talk about more explicit results tomorrow. So it's going to be 3 parts. I'm going to spend a little bit of more time motivating the basic philosophy, although I already said a few things. Then I will introduce the main tools for bootstrapping, which will be symmetries, singularities, and unitarity. And then I will give some examples, and I will surely not have time for all of them, in how to apply these tools to kind of reconstruct boundary correlators without any reference to the bulk spacetime. And so 2 references are, one, our lecture notes, but this part is very much still being written, so it's kind of a mess at the moment. But there was a white paper that we wrote together with other friends of ours that have been also working on this, that describes a bit of that literature. Okay. Okay, so let me say a bit more about the philosophy. And so let me first just remind you very explicitly what we usually do, okay, when we try to make predictions in physics. So we usually start with a set of physical principles, like we want our theory to be local, causal, unitary, and have some certain number of symmetries, okay? And then we try to encode those principles in a model or in a Lagrangian, okay? So for example, wanting things to be local will force you to introduce fields, yeah, with local interactions in the Lagrangian and integrating them over space-time volume and so forth. So there's a kind of a one-to-one correspondence between these principles and kind of just the Lagrangian that you write down, or the rules that you use for writing down your Lagrangian. And then you take that Lagrangian, you expand it in fluctuations around some vacuum, gives you equations of motions, you evolve them in space-time in perturbation theory, and you calculate using Feynman diagrams. That's exactly what we did in the last chapter when we computed the wave function of the universe in flat space and in de Sitter. We kind of followed that. We wrote down a Lagrangian. And it's so ingrained in us, we didn't even think twice about what type of Lagrangian to write down. Okay, it's just second nature. And then we use that to calculate some observables. Okay? And so this works really well if you have a well-established theory where you know exactly what the fields are and what the Lagrangian is, like the standard model in GR, for example. Okay? And you have many observables, because even in the standard model, in principle, this is an effective theory, And that defective theory would have an infinite number of coupling constants that you have to measure in experiment. Okay? So ideally, you have many different observables, like different types of scattering processes, different number of particles, different scattering angles, to disentangle kind of the coefficients of your Lagrangians, which are free parameters that you have to measure. Okay? So it works well if you have a, you know what the theory is, and you have many measurements to constrain the parameters of the theory. Okay? Unfortunately, in cosmology, we have neither. Yeah? So all the universe was at such high energies that we don't usually think the standard model is sufficient to describe it. And as we saw, we only measure a handful of numbers at this point. Yeah? We measure an amplitude of 2-point scalar fluctuations and a tilt, 2 numbers, in fact. And so it's really hard to reconstruct from 2 numbers, this ill-defined, high energy theory that we don't know. Okay. So what the bootstrap is trying to do is trying to get some different ordering in the space of theories from a handful of physical principles that we think are robust, that all possible models of the early universe somehow have to satisfy if they're sensible. Okay. But okay, before we get there, let me just actually say although this is straightforward to apply, this has some drawbacks, and some of them I have mentioned and some of them I haven't mentioned yet. So for example, as I already mentioned, especially for gauge theories, in order to keep the thing local and causal, you're forced to introduce additional gauge degrees of freedom. So for example, if you want to describe the 2 polarizations of a photon in a local theory, you have to introduce the 4-dimensional vector potential. And then you have to, make up a gauge constraint to remove additional degrees of freedom that you didn't want to have, and so on. Okay, so you're kind of playing catch up. But in the end of the day, you don't observe that stuff. And as I told you in this example of Park-Taylor, for example, the fact that you did introduce these redundant degrees of freedom was actually dramatically complicating intermediate steps of the calculation. Then often the relationship between Lagrangians and observables is many to one. So there's many Lagrangians that can lead to the same observables, often because of field redefinition. So Lagrangians are not field redefinition invariant, while observables, of course, are. And so even in scalar theories, this can happen. Yeah? Sometimes you can just write a free theory in an inconvenient set of fields that looks like an acting theory, and then you just keep calculating and you always find 0 scattering amplitude, and it just meant that you weren't looking at the right basis of fields. So things like that are manifest in an on-shell formalism, but they can be hidden in a Lagrangian. And then, as I said by now many times, that even at tree level for cosmology, we have complicated time integrals that we can't do. And then finally, even if we work hard enough and do these calculations, the fundamental principles that go into these calculations, like locality and unitarity, and in fact, somebody on Zoom kept asking about unitarity and so on. And okay, I was kind of brushing it aside and said, okay, it's all implicit in the Feynman rules, okay? But it's not manifest. Yeah? So it would be nice to turn around and know precisely at the level of the final answer what was coming from locality, what was coming from unitarity, and what features of the answer actually reflect that it was coming from a local causal theory. Or said differently, if I were to give you just now an arbitrary function of the energies of the external fields, how would you tell whether this is consistent or not? For example, for the S matrix, there's a simple check you could do. S dagger S equals 1. Yeah? So I give you an S matrix, you calculate S dagger S, and if it's not 1, you just tell me to go home. Yeah? And give you something better. Yeah? For cosmological correlator, I can give you a function, and you say, okay, maybe. And I don't know what to check. Okay? And so I will give you a few things that you can check in these lectures. Okay, and then finally, everything we said so far was just in perturbation theory. The ultimate dream, of course, is to derive some non-perturbative features and do things like DSCFT, where we need to define things more fundamentally. And so if you want to do something like this, or describe the UV completion of all of these correlation functions, you need some deeper understanding of what the fundamental principles are that these correlation functions should satisfy. So you're not going to discover the UV completion or the non-perturbative completion of these things by just slavishly going through all orders in perturbation theory and somehow waiting for a miracle. But I think you have to change your plan of attack and try to understand what constrains the space of all possible boundary theories. Okay. So what one therefore does in the bootstrap is to cut out the middleman. Don't write down a model, but try to go directly from physical principles which typically are only a handful of robust things. So you should not write down a non-local theory, yeah? Or you should not write down a non-causal theory and so on, because you would just, yeah. So you start from those principles and you try to directly infer what is the complete space of allowed observables given those principles, okay? So there's basically two challenges. One is to enumerate the set of physical principles that you need. And for the S matrix, for example, we know exactly what those principles are. Okay? For cosmology, actually, we don't know what the complete set of all principles are that we need to impose. And then the second step is you need to infer in perturbation theory, for example, how is each of these principles manifested in the final answer. And for the S matrix, we understand this relatively well. Not perfectly. We understand it at tree level completely, as I will show you. And at loop level, we understand it order by order, but like it gets successively harder. Okay? And we don't understand it non-perturbatively for the S matrix. And so, as I said, this is particularly relevant when you have many theories, like in inflation or in BSM physics, and very few observables, like in cosmology. Okay, so maybe I just stop here, and I will continue tomorrow by first describing in a bit more detail how this works for the S matrix, and then we will try to parallel that success for cosmological correlators. But I will stop here and take questions first. Thanks.
Questions?
Well, maybe this, I'm not sure how important this question is, but since you mentioned unitarity, you basically deal with one wave function, the wave function of the universe, right?
Yes.
So the test to test is that it's just normalized to one continuous as time goes on, or what?
Well, notice that we don't have time anymore.
Yeah. So
you could ask, for example, one notion of unitarity is that the norm of the wave function is conserved.
Yeah.
So that the wave function squared as a function of time is conserved, doesn't change with time. And you could ask, what does that mean for my boundary wave function coefficients? And in fact, that question has been asked and answered. I might have time to describe it.
I mean,
but
you mean there are still non-trivial consequences and constraints?
Exactly. Just like for the S matrix, unitarity, for example, has consequences for individual diagrams. So cutting rules, for example, that when you cut an intermediate line, there's certain discontinuities that you generate for the diagram that by unitarity are constrained in terms of lower point objects. Until recently, maybe 2 years ago, we actually had no idea what the corresponding constraints would be for cosmological correlators. And now we do. That's progress.
Okay.
But in perturbation theory, we understand what bulk unitarity, which is precisely the constraint that you mentioned, that the wave function squared, probabilities have to be conserved in time. And that translates into something very well defined on the boundary, namely cutting rules. So in perturbation theory, basically we understand the analog also of S dagger S equals 1 for the wave function. But,
More questions? If not, let's thank Danny again.
yeah, thanks.
So we'll have a photo session, right? Yeah. Let's follow the instructions from local organizers. Perhaps everyone should come to the stage or near the stage.
Move forward, and then speakers can sit here in the front and sit down, and then we make some rows, and then somebody will take a picture. Okay, guys. So after this, we'll have a lunch, and there will be a lunch ticket outside also.
Yeah, I think around half of the crowd can come. I mean, yeah, on the stage, come up.
So half of you could stay downstairs here, and the other half stay on the stage. So yeah, half of you please come down. 마스크 어떻게 하죠, 박사님? 마스크 벗어도 돼요. 예, 찍을 때만. 벗어야 되나요? 그러니까 사람들이 어떻게 생각할지.
자기 선택. You can take off your mask if you like. One more announcement. So from today onwards, we will try splitting into two groups for lunch. Yesterday, I think we had plenty of spaces, so maybe around 60 could join me for the first group, and then whoever is remaining could join Miok for the second group. Maybe the second group will start in about 15 minutes, and the first right now.
Neck. Okay. Maybe this is good enough. This is just no. I just yeah. Yeah, blackboard is yeah. I just see.
Let me try to put this on the.
Oh.
This is ridiculous, but this is the way.
Oh, okay.
Oh, put it here.
Oh, this way. Ah, okay. I didn't know that.
Such a simple principle. But you're putting on the back.
I see. Okay.
Right, that's
That-
all right.
I guess this makes more sense. Okay.
I
Okay.
was looking at it. There should be something better maybe.
Right. Right.
Hey, the point.
Yeah. Okay. Oh, we are moving this out, maybe. No. It's just a blackboard. Yeah. Well, just maybe use board a little bit like this.
You can using both of them,
Okay.
and they will move.
Yeah. Okay.
slowly,
That's fine. Yeah.
He will zoom in and out, so he will take care of it.
Uh huh.
But don't move so fast. Then he
Okay. Yeah, everything is set. Yeah. Okay. Great. Okay. Yeah.
So the technician said that the mic is not so sensitive.
Mhm.
So it should be the mic should be very close to.
Oh,
your
very
mouth,
close, very
otherwise
close.
The voice is not captured to this online speaker.
Maybe this is close enough. Is it?
Can you?
Yeah. Yeah. Test. Is it? Is okay? Yeah. Okay.
welcome to the afternoon session. So it's time to start. So Shinsei will continue exciting discussions in this second lecture.
Yeah, thank you. So yeah, welcome back. Last time, I started to discuss the reflected entropy in 1+1D system. So you can think of a lattice quantum system or quantum field theory in one spatial dimensions. Since I'm a condensed matter physicist, I'm used to think about spin chains. I have a one-dimensional lattice, and then spins are defined for each site, and then they may interact in some way. And then I made a distinction for two states. For the one class of state, I introduced the ground state of gapped quantum spin chain, gapped Hamiltonian. And then we could also have a ground state of gapless or critical Hamiltonian. And then for each case, we can discuss Markov gap. So remember, Markov gap is a difference between reflected entropy minus a mutual information. And then I first specify two subregions. Let's say region A, that is a part of this one-dimensional chain. And they also consider another part, let's say region B. So in principle, these two regions are separated to each other, but in the setup I'm interested in, these two intervals, they are adjacent to each other, and there's a third region, which is the region outside of this region A and B. Or if I use a periodic boundary condition, I think last time I draw a circle to represent the quantum spin chain with periodic boundary condition, and then I tripartite this chain into three regions, A and B, and then the remaining part is called region C. So we define the reflected entropy for two regions, let's say A and B, or we could do for other regions, but let's say we focus on region A and B. So I first trace out region C. So I first take a partial. We take one of these states, ground state of either gapped or gapless quantum many-body Hamiltonian, and then I start from some state, but then I trace out region C. Okay, so then we get density operator or density matrix supported in the region A union B. And then once we have a mixed quantum state, I think last time I described how we define reflected entropy for mixed quantum state, rho AB. And then I subtract a mutual information, which is just some combination of entanglement entropy for region A plus entanglement entropy for region B, or minus entanglement entropy for region AB. So that's a definition of mutual information. So we call this quantity a Markov gap, or I use H to describe this. So last time we argued that H is 0 for the ground state of gapped Hamiltonian, or actually to be more precise, H is 0 for short-range correlated state. So it can be something like a ground state of yeah, okay. So maybe I just say, yeah, I think it's good to say that it's a ground state, short range entangled ground state of gapped Hamiltonian. For that, H is 0. We made this argument by basically using the matrix product state representation of gapped ground state. Now we are going to discuss the second case, where we have a ground state of critical Hamiltonian. And then my main focus is the case where criticality is described by a conformal field theory. In condensed matter physics, critical point can be described by something other than conformal field theory. That's possible. But it is still true that many famous quantum critical points are described by conformal field theory of some kind. So I will consider conformal field theory ground state. Okay. So for the ground state of CFT, this H turns out to be universal, and then it is just given by the center charge of the conformal field theory, or more precisely, H is C over 3 log 2. Okay, so that is the, I think I already quoted this result, but now we are going to discuss more about this result. Okay. Yeah, so how do we understand this result? There are many ways, I mean, few ways. So this was first discussed by the paper Zhou, Shiba, Soejima, Mon, Zaletel. So they made the following observation. So let's consider once again this tripartition. See, I draw this way now. Okay. So let us focus now on the special case where the size of this region C is equal to the size of region A plus size of region B. Or if I have a lattice quantum system, number of sites included in region A plus number of sites in region B, they are equal to the number of sites in region C. Let's consider this special case. Okay. So then once I trace out region C, then once again we have a mixed quantum state rho AB. But now if you remember the definition of reflected entropy, so let me, since I traced out region C, now I have only region A and region B left. But now, if you remember the definition of reflected entropy, I first introduced the exact copy of A, which I call A bar. Maybe I use A star. I think it's more common notation. Then I have to also introduce exact copy of region B. So let's call it region B star. And then I have to write down a pure state on A star union A union B star. So I have to write down some state. I mean, I think following the previous notation, I have to write down some pure quantum state on this tensor product Hilbert space. And this state has to be designed such that once I integrate out A star and B star, I have to get rho AB. Okay, so this is something we call purification. Okay. So now as a first step to compute reflected entropy, we first need to find a canonical purification. But this UC Berkeley group, Zhou and the companies, they made observation that, wait, if you look at the original configuration, so I have a state psi ABC, and then once I trace out C, I get rho AB. So that means, and then we put this special condition where total number of sites in C is equal to the number of sites in A and B. So that means this original state, which is the ground state of conformal field theory, this is actually considered as a purification of rho AV by construction. Okay? So in this case, with this condition, we actually know what the purification is. It's just the initial ground state. Okay, so then I now draw this way. So I have a quantum spin chain A with region A and B, and they previously had this region C, but I can consider a part of the region C as the A star, and A and A star, they are the same size. And then I also consider B star, which is a part of C, but the B star and B had exactly the same number of sites. Okay, so I have this state psi. Yeah, so previously I wrote this as psi ABC, but this is, you can think of it as a purification. Let me write this rho AB. This is nothing but the canonical purification of rho AB. Okay, so then to compute refracted entropy, I have to compute a von Neumann entropy of A star by tracing out, I can write this way, von Neumann entropy of the reduced density matrix associated to a region A star where rho A star is obtained from the ground state psi by tracing out B and B star. Okay, so this is a particularly simple case where we actually don't have to find the purification. We already know the purification. And then we just need to compute the entanglement entropy of von Neumann entropy for this interval. Okay? Yeah, sorry. Right. So then H is nothing but SAA star plus SAB minus SA minus SB. So SAA star is the reflected entropy, but I have to subtract mutual information. So SAB minus SA minus SB is minus mutual information. So we just need to consider this linear combination of entanglement entropy computed for the ground state of CFT for these regions A star, AB, and A and B. Okay? So this is the canonical result. So if I consider CFT ground state, then we consider a single interval of length, let's say small l, and then maybe that I use maybe the capital L to describe the total system size. Then if this is a region A, entanglement entropy for this interval A, it's a famous formula, C over 3, C over 3, something like a log L. I think you may have seen the formula which may be looking like C over 3 log of L, where L is the, maybe I put A here, A is the length of region A, so it's logarithmic in terms of the subsystem size. But now, since I'm considering the case where the total system is compact, I have to modify this formula a little bit. So the more correct formula is log. Instead of putting LA, I put the quarter distance, which is sine pi LA divided by capital L. Okay, so this is the kind of standard formula in CFT. And then, of course, if LA is very small compared to capital L, this is basically the famous formula, C over 3 log of LA. Okay. So we can take this formula. I may say a few words about the derivation of this formula later, but once we know this formula, we basically compute C over 3 log sine pi LA plus LA star plus log sine pi LA plus LB minus log sine pi LA so this is the H, but so yeah, this is the kind of simple calculation. But now we have to remember LA plus LB has to be a half of total system. Okay. LA, yeah, it's because it's because of this constraint. The size of A plus size of B has to be exactly the half of the total system size. So if you remember this, and then use some trigonometric identities, we just get C over 3 log 2. Okay, so this is how we understand this result here. A question? Yep.
Ask, can the psi ABC, the dense matrix, not differ from the canonical purification by a unitary transformation? Psi rho,
So
that one, psi
so
ABC.
it may not be exactly psi, but the psi up to some unitaries. Maybe, but I don't expect it affects entanglement entropy. Yeah,
So-
good question. I mean, it is true that this is a purification, but one may wonder, is there unitarily equivalent purification? But I think it should not affect the result. Otherwise, we should worry about this even outside of this context, in fact. So I think this should be insensitive to the unitary ambiguity. Other questions? Maybe. Yeah, question. That's right. I did not write down outer. Yeah. That's right. So because we subtract two things, UV divergence cancel out. Yeah. So significant. Yeah. So I mean, first of all, it's a good thing because it's universal. Other than that, can we say a bit more about the significance of this? Yeah, I would say from my point of view, significant is a universality. Yeah. I mean, it's also surprising because one can also consider subtraction of this kind for other entanglement quantity. For example, you can consider negativity minus mutual information. They, after adjusting some coefficients, they both diverge in the same way, but we don't actually get the universal result for negativity. So it's not, subtraction is, part of the source of the universality, but it's not automatic. So it's a bit non-trivial. But yeah, but maybe somewhat more physical way to understand this quantity. But it's somewhat related to the question asked in the first lecture: is there operational meaning for reflected entropy? So if we have such a nice interpretation, we could develop more insight. But yeah, so far I could say this is just universal. There, other. So yeah, so for example, if you consider finite lattice system, it won't be exactly like this, but it's exact in the limit where basically I increase the number of points from but other than that, this is just this in the continuum limit. Yeah. Okay. And true for any CFT, there's no like 1 over C correction, whatever. This is true, just like this. Other question? Yeah. Yeah. So that's a somewhat difficult question for me to answer. So this quantity, this particular, I mean, combination, reflected entropy minus mutual information have been used, but Hayden, Parika, and Sauce gave critically looked at this quantity, and then I think they found out that it is the related to some property of the recovery process, and then yeah, sorry, I couldn't really explain this, but they gave this name Markov gap, which is yeah, which has some quantum information theory motivation behind. Yeah, yeah, but we don't use that type of description here, unfortunately. Other questions? Okay, so this is quite nice, although it's a bit limited to this special case. So I also want to give a bit more quantum field theory way of thinking about it. So it is known that entanglement entropy, let's say, yeah, let's start from entanglement entropy for a single interval as a warm-up. So I have some region A, and then one may, I think we already know the result. So the result is this famous result, C over 3 log x2 minus x1. And then, yeah, perhaps I have to also put ultraviolet cutoff. So this is the famous result. So this entropy, entanglement entropy, can be calculated from so-called a twist field. So sigma A. Right, so there's some formalism to compute this quantity. One is the replica trick. And then there's also something called the twist operator formalism. So with this formalism, we can compute moment of reduced density matrix by using some operators. Sorry, maybe not log. Log comes later. Sigma n. This is something called twist operator. And the minus n means anti-twist operator. So I will explain what this is. But there's a very convenient formalism which allows us to compute entanglement entropy or moment of reduced density matrix by using local operators, something like local operators. And then we also know
there is a question from
Yeah.
chat. Given that rho AB is a mixed state, is A star something that purifies the state you get by tracing out P? And similarly for P, I'm trying to understand the factorization A star cross P star.
yeah, sorry, I couldn't quite get the question.
Me neither.
Maybe I can quit that again. So factorization. A star something that purifies the state you get by tracing out B. Okay, so I guess maybe question, I think if I interpret, I guess question is, yeah, so I had C, but I didn't, but to purify, I need A star and B star together. And then I guess question maybe how do they, I don't know, come? Yeah, so this part I'm calling this, it's initially region C, and then it's now interpreted as A star union B star. I guess in this case, it's you should really think of this as like an exact copy of this lower part. I have a Hilbert spaces A and B, or you can think about this Hilbert space for the half of this chain, and then it's maybe a bit subtle to discuss factorization in the continuum limit, but if I assume it comes from the underlying lattice system, there must be some way to factorize this A and B. But once I understand how lower half is constructed, including how we factorize this lower half of the chain into two regions, then I just copy this setup. It's exact copy of the lower half. Okay, I'm not sure if it answers your question, but yeah, I guess if there's more questions, maybe you can we can discuss later. Other questions? Okay, so yeah, so there's a convenient formalism where we can compute the moments of reduced density matrix by using A operators. So this is called twist operators, and then N is replica index or Renyi index. And then since we are interested in trace of log low A log low A, but this you can compute by first computing the moment of a this trace of rho A n, which I just rewrite as E2n log trace rho A, and then take a derivative. And if I set n to 1 at the end of the calculation, I think I must put minus here. At the end of the calculation, we recover entanglement entropy. So log of something is a bit difficult to compute or think about if we want to develop path integral representation. But if we kind of use this trick to rewrite a log of rho A or rho A times log of rho A using trace rho A n, which is sitting here, once we first compute this and then take a derivative and then send this n to 1. So that is a famous trick called replica trick. So this is the first step of this formalism. And then second step is to consider to express the moment of reduced density matrix by using this local operator called twist operators. Okay, so this is actually the formalism, for example, that we can use to compute this quantity. And then I'm explaining this formalism for entanglement entropy for now, but this similar formalism can be developed for reflected entropy. But let me first say a few more words about entanglement entropy. So we are interested in, yeah, maybe I can first say, how do we convert this expression, trace rho A to power n to the twist operator formalism? So we consider a path integral representation of this object. So I start with some state psi. So let's say rho A. Yeah, so rho is pure state, for example, ground state of CFT Hamiltonian. And then state psi, you can prepare by using the imaginary time path integral from infinite past to let's say time, Euclidean time equal to 0. So I just do the path integral from infinite past to present. That prepare a ground state of the Hamiltonian of my interest. To write down a density matrix, I also have to prepare bra. So to prepare bra, I do path integral from infinite future to present. So if you wish, this is the path integral representation of the pure state of our interest. And then we have a region A of our interest. Let's say for the t equals 0 time slice, I have this region A, and then the rest, A bar, but I'm interested in this region. Okay. So to consider a rho A to power n, I consider n copies of this path integral. I think I used this stripe to represent my path integral. So this picture is drawn slightly different from this, but it's the same thing. Now I prepare n copies. And so on and so forth. I have n such copies. So then, since I'm interested in a partially traced density matrix, I do path integral outside of this region A. So outside of this region, everything is integrated out. With the path integral, except for this kind of slit region representing the region A at time t equal 0, and then to compute the product of rho A, I cyclically identify these upper and lower part of this slit. Sorry, this is not the right picture. So I identify field configuration here with field configuration here, and then I identify my field configuration here with the field configuration in the next copy, and then it continues such that this lower part of this field configuration is identified with the field configuration on the upper part of the last replica copy. So this is a path integral representation of moment trace of a reduced density matrix to power n. So this is the path integral. First step is to write a path integral expression for this. And then the second step is to fold this picture. So I now have a n copy, 1 up to n copies. But instead of writing these n sheets separately, I just put everything together. So I combine them to write a single stripe. But for here now, each copy, I have a quantum field for each seat. I call it phi 1 maybe for the first copy. I have a phi 2 for the second sheet. So they are like replicas of the original quantum field theory variable or quantum fields. But now, instead of considering each seat separately, I consider everything, all these quantum fields together. So I use maybe capital phi. Capital phi represents all quantum fields. So it's like n component fields living on a single seat. So this is, I don't know, more efficient way of representing this path integral. And then there's something happening here in this region A, interval A. So basically, we can understand this effect of this slit, which are glued together by using some local operator, which I call sigma and sigma bar. Okay. So these sigmas, they create some sort of branch cut. So as you move your field across this cut, it implements the effect of gluing this field configuration. Let's say phi 1 is identified with phi 2, and phi 2 is identified with phi 3, and so on and so forth. Okay, so we can consider a we can envision some operators creating such branch cut. Okay, so so in this picture, we are interested in writing some path integral, which is defined on this peculiar geometry, which has n sheet. I call it maybe Rn. So that's a very peculiar geometry where I have a n copies of sheet which are glued at this region A in some way, or we can write it as path integral of a single seat e2 minus s, which is the n copy theory. Maybe I use different notation. This is now defined just on the complex plane C, but now with two operators inserted. Maybe I write this sigma and sigma minus this way. Okay, so this is the basically how this twist operator formalism comes about, and then so just for 2 points, in order to evaluate this correlation function, basically the only thing we need to know is the dimension of this operator, and then it's a conformal invariance just completely fixes this 2-point correlation function once we know the dimension of this operator. So what is the dimension of this operator? I use Hn to represent the dimension of this operator sigma. So to compute the dimension, we can think about evaluating the once again the correlation function of twist field, but now with the additional insertion of stress energy tensor. Okay, because once we know this correlation function, using the basically the property of the stress energy tensor, you can write the differential equation obeyed by the sigma sigma correlator using the dimension of sigma. So basically from this, the behavior of this correlation function, we can read off the dimension of this operator. And I should also say that this is the correlation function of the replicated conformal field theory. So it's not the correlation function of the original theory, but I consider n copies of conformal field theories of my interest. And then I put everything together. So I just write it as n copies of tensor product of n product of conformal field theory. But to evaluate this correlation function, we can remember that this can be written in the single copy theory. So this is now, we are going back and forth between single copy language and the n copy language. But in this, yeah, I wrote down the two expressions here using the n copy theory language, CFT to power n language, and the original language. But in the original language, we don't use twist operator. So in the original language, we don't have to consider twist operator, but instead I have to consider conformal field theory on this peculiar space-time Rn. Okay, but now with additional insertion of stress energy tensor. Factor n comes from the fact that stress energy tensor of the n copy theory is the sum of each individual conformal field theory. So we just need to evaluate one point function of the stress energy tensor on this peculiar surface. But this we can compute by using the transformation properties of stress energy tensor. So we consider some transformation. I think it goes as this. So if you consider this type of transformation, this transformation transforms this peculiar manifold Rn to regular complex plane. And then under this transformation, stress energy tensor get transformed. But then there's a Schwarzschild derivative part. I think it may be something like this. So we just need to evaluate a Schwarzschild derivative. And then in turn, this evaluate this correlation function from which we know the dimension of the twist operator, which turns out to be this. Okay? Yeah, so knowing this dimension, yeah, so that was figured out long ago by Calabrese and Cardi. So I think most of the time I just use this result without actually ever thinking about how this dimension was derived. But this is for me an established formula, which means moment of the reduced density matrix, which goes as x1 minus x2 epsilon minus 4 hn. And knowing this result, taking a derivative with respect to n, and then send n to 1, you get C over, I guess you get C over 3 log this result. Okay, so this is the standard way of computing entanglement entropy in conformal field series. Okay, any question for this? And then now we want to do something very similar to reflected entropy. Okay, so we can basically follow this formalism, and then that was done by the original paper of Data and Faulkner. So they gave us how to use twist operator formalism for reflected entropy. And maybe I will first write the formula, and then I will say maybe a few words about this. So first of all, we need slightly more complicated replica formalism. So we have to consider a two replica index, which I call n and m. Okay, so it's not just a single replica index, but as it turns out, we need 2 replica indices, and then we have to also consider slightly more complicated. Maybe I write coordinate like this: y prime x2. So then the reflected entropy for these 2 intervals A and B, we first need to compute 4-point correlation function of twist field. Y GA GB GB inverse, and then we take a log, and then so replica index we have to send n both to 1. Okay, so maybe I should say a bit more about this. So first of all, why do we need 2 replica indices? The reason is because we consider square root of rho AB. Okay, so this is the purification of rho AB. That comes with a square root of original density matrix. So this square root, if you remember what we did, so we had this mixed state density matrix, but then we flip this ket to bra, bra to ket, but then we could put the square root here, and then square root is very difficult to express by using path integral. So instead of considering square root of rho AB, we can consider we can put some power here, m/2, and then we instead of having square root of this coefficient p, we put square root of the some power pi, this coefficient raised to power m/2. Anyway, so this replica index m is convenient to avoid having square root of density matrix. Okay, so we consider the m/2, which is integer. So when m/2 is integer, we can write down some sort of path integral representation for this, or density matrix associated to this state. Pretty much the same way we did for the entanglement entropy calculation. And then eventually, at the end of the calculation, we send m to 1 to reproduce the square root thing. And then a second replica is necessary because I guess we don't have it anymore, but yeah, actually we still have it because we still have to compute log of density matrix, which we get from this pure state, rho AB, this pure state. So we need 2 replica indices. That is the reason. And the second thing I need to explain is what are these twist operators. So these twist operators, conceptually, they are just very similar to the twist operator in the entanglement entropy calculations. But as it turns out, how we connect different replica copies is slightly more complicated. So maybe I will just explain that part a little bit. We are interested in deprecated version of of this path integral. So I first consider purification of this rho AB, but now it comes with this index M. And then I take a trace BB star. Right, so this represents rho AA star, but since it's a replicated version, I can put replica index M. But now I have to compute the von Neumann entropy of this density matrix. So in order to do that, I consider power n. And then I take trace of AA star. So then, from this, like we compute entanglement entropy from this quantity, trace rho A to power n. From this expression, we can compute reflected entropy using twist operator formalism. Yes, question? Right.
So that I was actually at the time I had a question on the boundary condition between the A and A star. You drew as if the A star is connected.
That's right.
So maybe it's in the natural boundary condition. But here, how do I see that it's A star? How can I think of this A star? How relation between A and A star?
Yeah. So that's actually a good question. And I think one way to think about this is that you can just consider a path integral. We first do the path integral for the mixed state. Maybe there's two things, A and B. But you can kind of fold. So this is path integral, and the path integral prepares pure state, but focusing on here and here, you get the mixed state. But you can think about, so in the previous case, we had the input field configuration, the output field configuration that I reconnected in some way. I think one way to think about this is that you can think about folding this picture here, like here, and then you have an input and output rec, but just think about both as an output rec. So you just map a mixed state to the pure state, and then you have n such copies, and then you start connecting them. But in the end, that picture I'm going to draw doesn't really do this folding explicitly, because in the end we just connect these things together to be consistent with this expression, and then we define some path integral in the end. So the end result is actually as follows. But this is actually a very good question. It's actually quite confusing point. But end result is as follows. So I consider, once again, many copies. I have a many copies. Actually, let me check my note here. Oh yeah, I draw this way. So I have a many copies. I have a m over 2 copies here. I have another m over 2 copies here, because I have a m over 2 copies for the bra and m over 2 copies for the cat. So I prepare many copies. So these replicas represent something hitting here. But now I have n copies of such things. So I basically copy this picture n times in this way. N. And so on and so forth. And let's say this is B and A. And then for region B, I just cyclically connect, like in the previous picture. So this is connected to this. This is connected to this, like this, and then continues. And then the lower bottom of this B is connected to upper part of this. But I have to do something slightly more complicated for region A. So this is connected to this region A. But by connecting this, eventually I hit the last copy of the first half of this M direction. Yeah, actually, maybe I put dot here. And then the lower part of this is actually connected to this part. And the B is always cyclically connected. Okay, so since I think the drawing gets too busy, I don't draw the connectivity for B regions. But B region is always just cyclically connected, like in the previous case. But A is actually connected to this part. And then I have A for the upper half, first M over 2 copies of A here. But then, once again, this copy is connected to this, and so on and so forth. OK, so this is the end result of kind of replica manifold. So we can write down the corresponding twist operator, which is denoted by the sigma GA and sigma GB. Okay, so and then yeah. Yes. Yes. Yeah. So this one continues like this, and then it goes back to this copy. Sorry, maybe this I should have written. So this goes like this, and then this once again goes, within this M over 2 copies, it's kind of regular connectivity. But once we hit this boundary, it goes to the next copy, and then we continue pasting, gluing, these copies, and then we go back to here. Okay, it's a bit complicated picture, but this was what was figured out by Dutt and Faulkner. And then we need to know the dimension of these operators. So the conformal dimension of twist operator GA is equal to conformal dimension of twist operator GB. And it's given by C over 24, I think M minus 1 over M times N. Okay? Okay, good. So this is the formalism, which allows us to compute reflected entropy. And then first, I did first computation first for 2 disjoint intervals. So A and B are separated by some distance. But if you remember the situation we are interested in now, we are interested in the case where A and B are adjacent to each other. But that we can compute reflected entropy for that case by taking the limit where we can consider merging these operators. We can consider the operator product expansion of twist operator here, which is the one end of region A. And then we take OPE with the other twist operator, which is the end of this region B. So sigma A in the limit where we consider the adjacent intervals, these 2 twist operators we have to combine together, and then it produces single twist operator with slightly different twist operator, which slightly represents slightly different connectivity. So I just use this notation where GA minus inverse and the GB are combined together, where I'm thinking of G and GB as a particular element of symmetric group GNM. Okay, because I have n times n copies, and then I can consider permutations in this symmetric group NM, and GA and GB a particular element of this symmetric group, and then precise form of G and GB we can read off from this picture. It's a bit complicated, but it's better to be explained by this picture. And then we can consider another group element, G inverse GB in SNM. That is the twist operator we need to compute this reflected entropy for adjacent limit. So we need basically a 3-point function of this. And then a 3-point function in conformal field theory, they are completely fixed by conformal symmetries. So we need to know the dimension of these operators, maybe x2, GA inverse GB. So we need to know a 3-point function of this kind. So the as we said, dimension of this twist operator and this twist operator, we know it's given by this. And then dimension of the operator in the middle, it was also computed. It's given by some formula like this. And then from here, we can basically compute reflected entropy once we take the replica limit. Okay, so that it's a bit maybe I'm taking too much time for explaining this formalism. But now we are ready to understand the origin of this C/3 log 2 result. So if we consider the difference between reflected entropy minus mutual information, knowing these dimensions, we can evaluate this 3-point function. But as it turns out, almost everything cancels between reflected entropy and the mutual information. However, we get contribution from the OPE coefficient. So when we collide these two operators, we create a new operators, but it comes with, I don't know, some sort of multiplicity. It's called OPE coefficient. So this a proportionality constant, we call it CNM. So we have a contribution from OPE coefficient, a log, and then limit n, m, both goes to 1. Yeah, sorry, I have to put the normalization 1 over n minus 1 log Cn m. Okay, so basically position dependent part, they all cancel, but order 1 part remains, and then that comes from this OPE coefficient associated this operator product expansion, which was computed, and then it is given by 2 times m minus hn, and then this is in fact C/3 log 2. So interestingly, this C/3 log 2 comes from the operator product expansion coefficient of of these twist operators. Yeah. So maybe I should write here. Yeah. So yeah, I should have written the here. Yeah. So yeah, we usually normalize 2-point functions, and then 3-point OP coefficient is, I mean, the 3-point function is normalization of 3-point is fixed, and this is given by OP coefficient. Yes. That's right. But here we just yeah. But this we don't have to use OP. By conformal symmetry, knowing dimension is completely fixed, and then this part x1, x2, x3 dependence. Just to make sure, this is x1, this is x2, and then this is x3. They are exactly cancelled by B, and then this OP coefficient is the source of universal contribution. Okay, anyway, this is a bit maybe technical. First derivation was intuitive. It was limited to the particular configuration where A plus B is exactly the half of the chain. This does not rely on there's no such constraint for the second derivation, so it's slightly more general. But anyway, I think these two derivations are also complementary to each other. Okay. Yeah, maybe I'm taking too much time for this, but is there a question for this 1D result? Okay. Okay, good. So now we discussed quantum mechanics, and then we discussed the 1D case. So then the next is to consider 2D quantum field theory. So I want to switch gear a little bit to discuss two-dimensional systems, or 2 plus 1 dimensional systems. But I will focus on the particular kind of 3D systems. So now I consider topological systems. So topological phases. I guess for field theorists, it may be better to say I'm interested in topological quantum field theory. So we can ask these multipartite entanglement in topological quantum field theories. Yeah. Yeah. That's right. So the holographic discussion was also in the literature, and then that was done by Hayden, Parikar, Soos, and then I don't remember the details of that paper, but they can basically derive this. Yeah. Okay. That's a bit mysterious how log 2 comes about, but it does come out. Yeah, in this derivation, it's basically these two sitting here. Okay. Okay. Other questions? Right. So I think one aspect of topological theories is that many condensed matter physicists are interested in topological theories because they support robust quantum phenomena, and then they support interesting excitations called anyons, and then there's even a idea of using topological systems, topological theories to perform topological quantum computations. But anyway, another aspect is that topological theory provides a very tractable setting where we can discuss a multi-party entanglement in many body quantum systems. I guess before discussing details, I perhaps give you some general properties of topological systems. So I'll be interested in two systems, quantum many-body systems in two spatial dimensions, and they I will consider fully gapped systems. So that means a ground state and excited state, they are separated by a finite energy gap in the thermodynamic limit. It means all correlation functions, all local correlation functions, they just decay exponentially, all correlation functions. So, from local perspective, there's not much life to discuss. No interesting correlation functions, but topological systems nevertheless have some non-local or long-range entanglement, which makes this system non-trivial, exponential decay. So yeah, since there's no interesting local correlation functions, there's no local order parameter. So that's also interesting from condensed matter physics point of view, because many phases of matter, like a ferromagnet or maybe even superconductor or superfluid, we have some way of describing them using order parameters, but topological systems, we don't have a local parameter, local order parameters. So that's actually the one motivation to look into something which are related to entanglement, quantum entanglement. So they may capture something we cannot capture by local correlation functions or local order parameters. So something I already said is that about excitation. So excitation, they are interesting because they may obey a exotic form of exchange statistics. So these excitations are called anyons. So if I consider local excitations, let's say excitation near this region, and there's another excitation here, and then you can think about adiabatically moving that excitation. So starting from some state with two excitations, let's say, if you move these excitations and the exchange their positions, if these excitations are fermions or bosons, we get either plus or minus one sign here. But in topological phase, topologically ordered phases, we get somewhat more exotic possibility where this exchange phase is something other than 0 or pi, or in some case, we actually get a different state. Maybe I'm writing some linear superposition. So starting from some state, since these excitations, in terms of spatial locations, they go back to the original location, or or maybe they don't go back to the initial position, but locations are the same. But quantum state may be still different. In that case, this is even more exotic than just the fractional exchange phase we get here. So this type of anyons are called abelian. But we can also get the non-abelian anyons when we don't get we don't recover the initial state by exchanging these particles. Okay, so I guess I can continue describing more, but these are some of the most important properties of topological phases. I guess I have 5 more minutes or so. Yeah, so yeah, maybe I say just a few more words, and then I think maybe the detailed discussion has to be in my next lecture. So as I said, there's no local order parameters, but we may still be able to characterize and distinguish different topological phases by looking at, for example, the entanglement entropy of topological systems. So there's a concept of this topological entanglement entropy. So idea is very similar to what we discussed in 1D. So I just consider some spatial region A. Yeah, okay, so I start from the ground state. It doesn't have to be ground state, but let's say I start from the ground state of a topological system defined on a two-dimensional plane, or maybe some other spatial manifold. But let's say to be simplest, we consider just a ground state on the plane, and then I bipartition this plane into two regions, A and the rest, A bar. And then once again, we can look at a von Neumann entropy for the reduced density matrix in this region A. It is known that this entanglement entropy to leading order, it scales as the size of the subsystem A. So this is called area law part. But in topological system, it was discovered by Kita Preskel and then Levy and Wen that there's a sub-leading constant term which is universal. So this part is called topological entanglement entropy. And then this captures the universal properties of particular topological system or topological quantum field theory. So in 1D, we get this logarithmic scaling, and then the coefficient in front is universal, and it captures the central charge of conformal field theory. In topological theory, this constant piece plays a similar role. It's a universal part, and then it captures universal properties of topological system. It's called topological entanglement entropy. Okay, so this has been known for a long time, but the problem, not problem, but caveat of this quantity is that it doesn't fully distinguish different topological systems. There are two distinct topological systems which are distinct. For example, we know it from the properties of the excitations, anyons in these topological systems. Yet they may share the same topological entanglement entropy. So there are some phases which we cannot distinguish just by looking at this topological entanglement entropy. So we may be interested in finer probe to distinguish different phases. Okay, so with that, I think I conclude for my second lecture. And then I will take questions.
Now the talk open for questions.
Yeah, this last point you mentioned, is there any connection between this and the sphere partition function?
Sorry, I could not hear you.
Is this related to the sphere partition function of these two
Yes,
class
this
one?
is a sphere partition function of topological quantum field theory. So it's a partition function of S3, yes. Yeah. This is not universal because I have to put cutoff here. So it's as you shift cutoff, it affects this part. So area part is not universal.
questions? I think I still didn't understand the replica part. N,
Okay.
M, N, M.
Yeah.
Will you repeat again? Sorry.
Right. It's actually quite complicated. So yeah, sorry, I didn't do a perhaps very good job. But yeah, so I think we do agree that we at least need one replica index because we are interested in log of something. Log of So we start from this pure quantum state, and then we consider a density matrix associated to do this, and then we take a trace. So this is my rho AA star, but we have to compute rho AA star log rho AA star. Sorry, AA star. So we need a one replica index to overcome log. So that's something I call n. So I consider rho AA star power n, and then trace. So that's the origin of the first replica index n. But as it turns out, we also want to do something with the square root having here, because we want to write down some path integral representation, and it doesn't come naturally with this square root. So we basically change this part to overcome this. I'm not sure if it's
how about the connection? M is is a cyclic.
Yes.
N is
so that's what actually I just quoted the final result. But to figure out that the connectivity, I'm not sure if I can do this on the fly now. But we need to follow. We need to look at this. I don't know, microscopic non-field theory description. That we have to think what it means. It is encoded in this, how we take trace and how we multiply these things.
Okay.
Yeah.
There is one question in the chat from the Sang Jin-shin. He said, I thought area law is one of the main information. So what it means by non-universality, and what should we take out of this result?
Yes, so I guess just from the scaling of entanglement, we may be able to distinguish different phases. So from that point of view, area law is in some sense it's a main behavior, but it's the coefficient in front of area law is not universal. And then this universal part is for example useful. For example, if you have a very complicated Hamiltonian, and then let's try to solve this Hamiltonian by computer, and then computer gives you some result, but then one may be able to get topological ground state, but we are not sure. So this gives as a kind of a probe for topological ground state.
And there is another question by Takato Mori. In the replica calculation of reflected entropy, do you expect any replica symmetry breaking?
Yeah, that's a good question. So, well, short answer is that it's not a priori clear under which situation, under which condition we get the replica symmetry breaking. In the reflected entropy calculations, I actually not sure. In the replica calculation of negativity, there's the sometimes we have to worry about the replica symmetry breaking. But for refracted entropy, I'm not sure. Yeah, so it's not clear. Yeah, but I guess we usually try some calculations and then we kind of check this result from different perspectives, maybe either using holography or field theory or some quantum mechanics, and then there's no convenient scheme to diagnose the replica symmetry breaking, but sometimes we have to worry about it. So short answer is I don't know. Yeah, but I guess in this case I do believe that replica symmetry breaking does not happen, but it's not a priori clear.
A follow-up question, what does it mean?
Replica symmetry breaking?
Yeah, here.
Right, so here, for example, it can happen in the calculation of large N theories or gravitational theories, and then you have to pick up some saddle point, but saddle point may not respect the symmetries among replicas or something like that. Yeah, so yeah, but not in this So yeah, what do we mean by replica symmetry breaking in this context? I think there may be still some meaning, but it's particularly clear in this large N type calculations. Yeah, but here not here. Yeah, I guess. Yeah.
More questions?
I guess what it means maybe is one aspect is that you may not be able to analytically continue your finite replica results to the replica limit, for example.
Can you say a few words about the topological entanglement entropy and the Bekenstein-Hawking entropy, since they are both the area?
Sorry, I couldn't hear the last part. Topological entanglement entropy
and the area law in black hole, like the Bekenstein-Hawking entropy.
I cannot say much, but there's a few papers relating topological entanglement entropy and black hole entropy. That was done by our department head, Hermann Farlinde. So I think one way to do this is that you can formulate gravity as a 3D gravity as a Chern-Simons series, and then it's a non-compact Chern-Simons series, and you can write down the entanglement entropy for this gravitational Chern-Simons series. But there's some way to rewrite this gravitational. So typically this, yeah, so I didn't tell you the meaning of this gamma. One meaning is that the partition function S3, but it is kind of meaning of total quantum dimensions, which somehow measures the
Azimuth excitations,
degrees of freedom in the topological series. But in the gravitational Chern-Simons theory, you have some way to rewrite it as in a more geometrical way, and then you can sort of identify this as a the area of horizon and so on and so forth. And there's another recent paper on this subject by Gabriel Won and companies. But yeah, I don't know much about this, but some people explore the connection between topological entanglement entropy and the Bekenstein-Hawking entropy.
Okay, I see. Thank you. Thank you.
Any questions? Further questions? If not, let's thank speaker again. Thank you very much.
공쇼 다음에 피자에서 그 포스터 세팅 있고 다음에 내일 모레
Yeah. Okay. So today, after this lecture, we're gonna, as announced before, we're gonna have a gong show from 3 o'clock. 3:50. Okay, sorry, 3:50 exact. Okay. Um, so you could check the list of Gong Show speakers. So please, all the speakers prepare for your presentation. The presentation files will be put up very soon. And after the Gong Show today, we're gonna have a pizza party. Okay. So we are not going to the restaurant in the other building today. So we're gonna have pizza here, right? Okay.
예, 한 번씩 1분씩 한 사람씩. 여기서 그냥 이 자리에서 하고 어떻게 하나? 여기서 이 자리에서 하고 여기서 내려가야 할 거야. 왜? 얼굴은 별로 안 나와도 저기 화면.
아, 저 화면만 나오면 되나요? 얼굴은 안 나와요.
화면 옆에 또 띄우던가?
지금 저기 오른쪽 위에 보이시는 게 지금
예.
저기 카메라로 잡은 건데 혹시
카메라 잡을 필요 없어. 얼굴만 잡고 요건 바로 요건 옆으로 띄우면 되는 거잖아. 옆으로 그 스크린 띄웠으니까. 예. 예. 요건 따로 띄우고.
그게 녹화에서는 이게 안 나온다고 합니다. 이게
뭐?
녹화할 때는 이게
지금 요거 근데 줌에서 레코드 하고 있지 않아요? 줌에서 실은 근데 유튜브에는 나중에 올릴 때는 유튜브 채널에 올라가는 게 아니라 줌 걸 올려야 돼. 줌 게 더 중요하지. 그렇잖아요.
그러면 그 레이저 포인트로 이쪽을 가리키는 거는 또 안 나와요.
아, 됐어. 뭐 그런 거지.
박상훈 선생님이
예?
줌 참가자분들을 조금 이렇게 하면 좀 안 보일 수 있다고 괜찮냐고 하시는데
무슨 참가자?
참가자들이 프로 발표 자료를 볼때 그 레이저 포인트로 가리키는 이런 걸 잘 못 보잖아요. 그럼 상관없어요.
아, 요건 잘 보여. 그거 뭐 그거 1분이기 때문에 뭐 just come and go. 그거 밖에. 예. 예. 그 유튜브는 그 저거 뜨는 거죠? 예, 그럼 되고 그다음에 줌에도 잡히는 거고. 그럼 합쳐 가지고 그 올리면 될 것 같아요. 그래가 잘 적절히 해 가지고 줌이 주가 되고 그다음에 그 유튜브 지금 잡히는 것은 적절히 해 가지고 그 각 프로그램별로 그 채널을 만들어 가지고 그 인터넷 그 유튜브 저희한테 보내주면 아마 저희가 유튜브에 또 올릴 거예요 아마. 예. 아니 저쪽은 다 이미 이해가 됐을 테니까.
Okay, all the Gongshow speakers, would you please come over here? Okay. So the order of presentation is just as given here. So Pratik Nandi is the first speaker, and then Jonathan Harper is the second speaker, and so on. So would you please, in order to save time. And then Kai Wen is the third speaker, and so on. So Pratik is okay. So please, because you are number one, just please here. And then Jonathan, and then 이게 파일이 아니 엑셀 파일. Okay, so I hope you know roughly, I mean, when you are going to speak. So the presentation file will be up. Yeah. Okay, so why don't we just start now? So we put up the. 여기요? Okay. So you're gonna have a microphone and a pointer. 이게 7번이잖아요. 1번으로. 넘버 1. 다시 거기 스페이스. 아닌데 문제가 생겨. Yeah, laser pointer.
Okay. Hello. Okay. Good afternoon, everyone. I'm Pratik Nandi from YTP. So my poster is concerns about this operator growth hypothesis for open quantum system. So there's many aspects of operator growth in this market. So operator growth concerns how a local operator becomes complicated under the time evolution of Heisenberg time evolution. This means how your local information spreads along the full system. So it's few years back, okay, so this gentleman proposed a universal growth hypothesis, which concerns that your operator growth can be characterized by a set of coefficients known as the Langevin coefficients. This is an asymptotic behavior of such coefficients. And based on these studies on spin systems and SYK, they proposed a chaos bound and generalized version of chaos bound and which concerns also the holographic side in the systems. So we extend this hypothesis from this by this spin systems on the studies of spin system and SYK, and we got a set of coefficients along with these coefficients over, and we also generalize such bounds such in chaos and holography. So okay.
Hi everyone, my name is Jonathan Harper from YATP. So many of us are familiar with the Ryu-Takanagi formula, which allows us to calculate the entanglement entropy for holographic spacetimes. But there's another formulation called the bit thread formulation, and this involves using some tools from convex optimization, which allows you to turn this minimization problem into a maximization problem. So in the bottom left here, what I'm showing is a maximal configuration of these bit threads, which are simple curves from region A to its complement, which take up a finite amount of space, have a finite thickness in the bulk. So the maximum number of these threads we can put from A to O is exactly equal to the area of the RT surface. So the RT surface acts as a bottleneck for the flow of these threads. So in my poster, I'll be talking about a generalization to multipartite entanglement where we consider many boundary regions. And in this case, we need to introduce more complicated objects, which I call perfect tensor hyperthreads. And if you're interested, please come see my poster. Thank you.
Oh, hello, everyone. I'm Kevin from KIAS. I will report a recent work joined with Professor Kim Yong Lee. So in 2018, Harvey and Wu proposed a new hack operator, which connected the characters of 2D bosonic rational CFTs. We recently generalized this to the fermionic cases, where the NS characters are connected by a new hack operator called TPF. And this can also be generalized to the NS tilde and R sectors. We found that almost all known supersymmetric rational CFTs can be realized as the fermionic hack images of some simple supersymmetric minimal models. For example, here I list some simple examples. For more examples, please come to my poster. Thank you.
Hello, everyone. I'm Si Do from Kobe University. Today, I'm going to talk about super heavy dark matter production from symmetry restoration first order phase transition. So we consider two-field inflation model. One field is the phi, which drives inflation, and the other field is the sigma field, which is a spectator field. And during inflation, this first order phase transition may happen in the sigma sector, and the dark matter and the gravitational wave are produced simultaneously. And our main result can be found in the left panel of the plot. And the height of the gravitational wave signal is related to the latent heat released during inflation, and the frequency of the gravitational wave is related to the Hubble parameter during inflation. And after inflation, the symmetry restoration of the sigma field happen, which protect the dark matter and sorry.
Hello everyone. My name is Ryotaro Ishika from Tokyo Metropolitan University. And my talk will be based on a recent paper in collaboration with Shuntaro Aoki and Sergei Ketov. And our goal is to get a viable inflationary model with primordial black holes production in supergravity. And we generalize Chakotay-Kalos's model, which is a supergravity extension of the Stravinsky inflationary model by adding a holomorphic function to its superpotential. And next page. Next page. Thank you. And yeah, these are the results. And as a result, our supergravity, our model has a viable double inflation and compatibility with CMB observations, and has a short ultra-slow stage and can generate PBHs. Thank you for listening.
Okay, so hello. Okay, so I'm Warafat Pyunsuk. I'm from Sokendai KEK, Japan. And so in this work, we basically want to study the superstring theory, which can address many questions like how the universe begin. And so, but the string theory requires extra dimensions. So this will lead us to the non-perturbative study of the compactification of extra dimensions. So, but here the IKKT matrix model can provide such a non-perturbative construction to the superstring theory. And you, that's not all. This is not mine. But this is not mine. There are 2 pages. Hello again. Yes, okay, thank you. Okay, yeah, and so there are many numerical studies that has been used to study the model, and recently it was suggested that the mass term was needed to be introduced to realize the real and Lorentzian spacetime. Otherwise, we're gonna get a Euclidean and complex spacetime instead. So in this work, we study the IKKT matrix model with mass term using the 1/d expansion as an analytical approach, and we found some agreements as well. So thank you.
I changed slide. Okay, hi everyone. I'm Aaron. I'm a postdoc at Kyunghee University here in Korea, and I'm going to be talking a bit about building a realistic neutron star from holography. So the main aim that we're trying to answer this work is to understand the physics of dense QCD, And neutron stars provide a sort of window into this region of the phase diagram. They're also in a region where we don't particularly have good QCD techniques. So our idea was to use holographic duality to model QCD as the dual theory to some weakly coupled gravitational setup. And the gravitational setup we choose is one called the Witten-Sakai-Sugimoto model. It has only two free parameters, the 't Hooft coupling and the Kaluza-Klein mass scale. And the sort of punchline of our work is that the stars we construct using this holographic QCD are able to satisfy all the known astrophysical constraints provided by LIGO and NICE emissions, etc. So come and see my poster and ask questions if you want to hear more details about this. Thank you.
Hi, good afternoon, everyone. My name is Jianming from YTP. So today we'll talk about our recent work. We call it complexity equals anything. So the first thing I want to advertise is from the viewpoint of the quantum information or quantum circuit, the definition of the complexity actually is ambiguous. It depends on the choice of the gate, and also especially depends on what's the cost we assign to the gate. So it's not just a number. And in this work, what we did is like we show in the gravity side, you can find the infinity gravitational observers, which could be defined on the quantum 0 subregion or even quantum 1 subsurface. All these observers actually could be considered as holographic dual for the complexity because they all grow linearly in the late time and also present the switch-back effect in the Shockwave geometry. That's all.
Hi, I'm Mitsuhiro Nishida from PostTech. So we studied a relation between Ledger conformal blocks, which are building blocks of OTOC in CFT, and pole skipping points, which are special points in momentum propagator. And the keywords in my poster are OTOCs, or quantum chaos in CFTs, and the gravity duals of Ledger conformal blocks by using ADS linear coordinates, and pole skipping points in CFT momentum propagator. So if you are interested in these keywords, please come to see my poster. Thank you.
Hello, I'm Li Jinyang from KK. Actually, everything I want to say is contained in my title. Baryon production works well in QCD. We introduce a linear sigma model at QCD epoch, as you see in the first figure. With the sigma evolution, the baryon number is successfully product. And if you want to fit the variables in all this, we need to, maybe we can to introduce some dark matter and some CP validation term to fit that baryon symmetry. But that's not doesn't too important. The key point is baryon production works well in just QCD. Yeah, thank you.
How to change the slide? Oh, okay.
And so
That's not my. The previous. Schumann.
Yeah, the first slide. Okay. Hello everyone, I'm Budayate from IISc. So I'm going to talk about bulk reconstruction in a non-normalizable mode on my poster. So the goal of that is effectively to understand the structure of waves, solutions of wave equations in ADS spacetime. So a way to do that is the bulk reconstruction procedure, which Chris spoke about a little bit today. So given that this is a solution of a second order wave equation, the usual bulk reconstruction is done only for one of the solutions. So we considered the other solution and considered both of them on the equal footing. And we achieve, in that process, what we achieve is that we consider two different representations of the empty ADS spacetime in global ADS and Poincare ADS. And we put the results for that we get from bulk reconstruction here on the same footing. Go to the next slide. Yeah, so effectively what we cover in this is a bunch of stuff where we consider Green's functions, mode sums, spatial prescriptions, and some generalizations of Witten's arguments. Okay, thank you very much.
Hello. Sorry. Good evening, everyone. I'm going to talk about the quantum black hole entropy in Einstein-Maxwell-Newton model. So we all know that the Bekenstein-Hawking entropy formula describes black hole entropy classically at tree level. But when people tried to compute the quantum corrections to this formula, it is found that the logarithmic correction is the most leading and universal. In this motif, we have computed the logarithmic correction to the entropy of asymptotically ADS and flat black holes embedded in four-dimensional Einstein-Newton model. These models are the most common building blocks of compactified or low-energy string theory model like the supergravities in 4 dimensions. So we found that in contrast to the flat black holes, the results for ADS black holes are non-topological, which provides a much wider infrared window in understanding the microphysics of the corresponding black holes. Thank you. Thank you. For more details, please come to my poster session.
Okay. Good afternoon, everybody. I am Pritam Nanda from Science of Nuclear Physics, and my talk is super translation transition between quasi-local black hole. As we know, in a recent proposal, Hawking, Perry, and Straubinger says that the possible resolution of information loss problem might be the presence of the more hair on the black hole, and those extra hair are related to the BMS symmetry. That's the asymptotic symmetry of a asymptotically flat space-time. Inspired by those symmetry, we have studied the symmetries of the horizon, basically the isolated horizon, kind of a quasi-local horizon, and we saw that although there is a similarity between the isolated horizon and the asymptotic boundary, but we realize only the super translation part of the full group, and also we study the evolution from one isolated horizon to another isolated horizon differ by a super translation could be happened by through a dynamical part, and here is the pictorial view of my work. So delta 1 and delta 2 are the two different isolated horizons. Okay.
Hello, my name is Yuma Furuta at Kyoto University, and my research of this archive number, is based on the construction of Narayan CFT by using a quantum error correcting code, which was found by Dematsky and Chappell in 2020. And in this construction, Narayan CFT with a high spectral gap corresponds to quantum error correcting code with high binary distance. But this distance is unfamiliar to us, so I found this quantity is equal to EPC distance of Boolean functions. And to make this large is also challenging problem, but I found a partial solution in so-called nested Click graph. For more details, please speak to me because I don't have poster. Thank you.
Hi, my name is Tewano from Gyeonggi University, and my poster is about the construction of covariant worldline action from quadrant orbit. So worldline particle models play important roles in various contexts of physics, but the construction of the worldline particle for the spinning particle are non-trivial. So we developed a general construction of manifestly covariant worldline particle action for any particle types in any space-time. For this, mathematically, we used the quadrant orbit method of the isometric group for the generality of the particle types. And physically, we used the Hamiltonian constraint for manifestly covariant. And the final action have the dual symmetry between the isometry and the constraint. So to see more details, please visit my poster. Thank you.
My name is Takumi Oikawa from Sokendai KK. I will focus on the relationship between the supersymmetric gauge theory, which is called Seiberg-Witten theory, and the monstrous moonshine phenomena, which is a connection between the modular objects and finite groups. And the Seiberg-Witten theory is a low-energy effective theory of 4D equals to 3D gauge theory determined by this prepotential. But this prepotential includes non-perturbative contributions, so it is difficult to compute directly. However, the prepotential is calculated explicitly via the Seiberg-Witten curve. In our work, we use the modular J function, which is related to the monstrous moonshine, and we obtain the instanton expansion of the prepotential Fk, including the monstrous moonshine coefficients. That's all. Thank you.
Good evening. My name is Vaishali Roy. My poster is about OTOC in driven CFTs. So this out-of-time order correlators has mostly been studied in thermal equilibrium cases. Out-of-time order correlators have mostly been studied in thermal equilibrium cases. We study OTOC in a non-equilibrium setup called periodic drive protocol, where the Hamiltonian is deformed such that the unitary operator, evolution operator, is generates some obvious transformation. Such a dynamics leads to three distinct phases, like heating phase, non-heating phase, which is separated by a dynamical phase boundary. And this can be demarcated using different size of Casimirs of the SL2R algebra. So our main result is that in large CFT, we show that OTOC shows exponential behavior in the heating phase, but only for a particular range of initial positions, which is bounded by the fixed point of the Mobius transformation. In a more recent work, we found the bulk dual of this driven CFTs. Okay. Please come to visit my poster.
Hello everyone, I'm Ashutosh, I'm from KK Sokandai. And the topic that I discussed in my poster is the numerical sign problem in quantum field theory. As you might know, many problems in theoretical physics are formulated in terms of multivariable integral with some weight. So if the weight is positive semi-definite, we can regard it as a probability distribution and perform the Monte Carlo calculations based on the idea of importance sampling. But the problem arrives when the action is complex. So there are a lot of theories in literature that have complex actions, like Hubbard model, the matrix models, SYM theory. So for complex actions, we cannot use our usual Monte Carlo method. For these theories, we have to switch to other methods. There are various methods like complex Langevin, Lefschetz-Thibault, analytical continuation. Every method has its own limitations. So I am currently working on the Lefschetz-Thibault method. Next slide. Yeah, so in Lefschetz-Thibault method, we deform our integration contour in such a way that the complex part of the action remains constant on the new integration surface. That is that new integration surface called as the thimble. And thank you.
Thank you. Hello, I'm Min Sung from Postec. And one question I try to answer is counting the states in higher dimensional theories, higher dimensional field theories defined on 5D and 6D. And there is some known method, such, for instance, you may heard about the ADHM construction of instanton moduli space. But I would say that there is an alternative, easy and powerful method called the Bloch equation. Using the Bloch equation, we can find BPS spectrum of arbitrary 5D and 6D supersymmetric quantum field theories. And we now generalize this Bloch equation into another kind of theory, 6D little string theories, which is not a local quantum field theory, but looks like a string theory. So this paper will appear in archive within this week. So if you are interested in Bloch equation, please discuss with me, and also please check the archive. Thank you.
Hello, I'm Stephen Angus from APCTP. I'm going to talk about fractons from a symmetry principle. So what is a fracton? Basically, a fracton is a particle that cannot move in any direction. And recently, many exotic phases of matter have been discovered, including fracton phases, which can be gapped or gapless. So in particular, gapless fracton phases require exotic gauge theories. For example, symmetric tensor gauge fields, where the spatial components are symmetric tensor rather than usual vector. Now, from a modern perspective, gauge theories can be realized from the perspective of generalized symmetries. For example, Maxwell theory can be realized by spontaneous breaking of one-form symmetries. And we might ask, is there a similar construction for gapless fracton phases? Can we characterize them in a model-independent way? The answer is yes. We need to use one-form symmetries whose charges do not commute with translations, which we call non-uniform symmetries. And mobility restriction is completely specified by the symmetry algebra. This gives a systematic method for constructing fracton gauge theories. Thank you.
Hi, I'm Shubhayu from Nicer, India, and I'm going to talk about our work on entropy current and fluid gravity duality in the Gauss-Bonnet theory. So under the linearized approximation, the second law of black hole thermodynamics can be expressed as the non-negative divergence of an entropy current. And in our work, we have tried to dualize this horizon entropy current to a fluid entropy current for the boundary fluid on the boundary of an asymptotically ADS black hole metric. For Einstein gravity, this boundary entropy current can be expressed completely in terms of the fluid variables, and it matches well with the previous results. But for other generic theories of gravity, it can be shown that the dual current is not entirely a function of the boundary variables, but also contains some data from the mapping functions of the horizon to boundary coordinate transformations, and those are not fluid data. And for the Gauss-Bonnet theory, we have checked that up to first order in derivatives, the Gauss-Bonnet term does not generate any extra contributions to the entropy current, but there are non-trivial corrections in the second order. So please come visit my poster. Thanks.
How to change the pages? Oh, okay, I see. Hello, I'm Zhizhen from Trinity College Dublin, and I will introduce a general strategy to evaluate the topological correlators, especially the Coulomb branch integrals of NX2 star SE2 super Yang-Mu theory on the generic smooth and compact form manifold X. Firstly, the NX2 star theory includes one NX2 vector multiplet, which consists of the 40 NX2 super Yang-Mus and one NX2 hypermultiplet with one pair of adjoint scalars with mass m. The generic form manifold is not necessary to be a spin manifold, in which case we argue that the extra spin C structure that is canonically defined by an almost complex structure is needed for the topological twist. Based on these facts, we show that the NX2 star interpolates between NX2 pure flavor Yang-Mus and the NX4 super Yang-Mus under certain limits. This is manifested in this table. We have reproduced the Waffle-Witten invariance and Dunston-Witten invariance in the massless and heavy mass limits, respectively, by explicitly evaluating the Coulomb branch integral. Thank you.
Hello everyone, this is Kaberi. I'm from Chennai Mathematical Institute, India. So my work is based on the study of quantum extremal surface and islands for a small Schwarzschild de Sitter black hole in a 4-dimensional background. So we have considered the limits in our case, which is basically the mass of the black hole is considered to be much less than the de Sitter scale. Which turns out to be the temperature of the black hole horizon is much greater than the de Sitter temperature, which is basically we have a small Schwarzschild de Sitter black hole in a frozen classical de Sitter background, which is far away from the black hole horizon. So in this case, if we try to calculate the entanglement entropy for the bulk matter, which is outside the black hole horizon in the static patch, then it shows unbounded linear growth in time, which is the information paradox for this background. Now, if we consider some island contribution across the black hole horizon, the total entanglement entropy for the bulk matter becomes time independent, which recovers the page curve at late times, and the island boundary turns out to be just outside the horizon. So please come to my poster to see the details of this.
Hello, everyone. My name is Vineet Krishna, and this is I'll be presenting on a work I have recent work with Abhijit Gadde and Rakshu Sharma. Next. And in this work, we have introduced a new multipartite entanglement measure called multi-entropy, which has the following interesting properties. It is symmetric with respect to all parties involved, like von Neumann entropy, and it reduces to the von Neumann entropy for the bipartite case, and it can be defined for any number of parties. Finally, the most interesting of them all is that it's for holographic CFTs with large central charge, it can be computed by the area of an appropriate soap film anchored on the boundary. So the definition for the way we define this entropy is by using replica trick, where we identify the connections made with n square number of replicas, and then we take the n approaching one limit to define this entropy. Next slide, quickly. Yeah. So the dual of this multi-entropy is given by the area of the web. And if you have any more questions, please do contact me and see my poster.
Hello everyone, I am Surajit বিশ্বাস from IISER Bhopal, India. So I am going to talk about the dual theory for maximally n extended supergravity theory. So basically we considered the bulk symmetry algebra for n extended Poincare algebra to write down a Chern-Simons theory in 2+1 dimension. And in 2+1 dimension, the Chern-Simons theory is equivalent to a gravity theory. And we basically use the Chern-Simons to Weismann-Witten model correspondence to write down a 2D theory for gravity. And we have found that if we want to write this Weismann-Witten form, we have to consider the internal automorphism group to be SON. And its asymptotic algebra is a suitable flat limit of this OSP group. So these are some references. Please visit my poster for more details and warm discussions. And thank you for your attention.
Hello everyone, I am Tabassum Renuma from IISER India. Here I am discussing about the asymptotic symmetries from celestial CFT, and this is the holography on celestial sphere which describe the 4-dimensional physics in terms of 2-dimensional celestial conformal field theory. We are using this technique to find the asymptotic symmetry algebra. Next please. For the n equals to 8 supergravity theory, here we are using the double copy formalism, where the n equals to 8 supergravity amplitude can be expressed in terms of n equals to 4 super Yang-Mill amplitudes. And we are using the double copy formalism in soft and collinear sector and find out that the extension of SU8 R symmetry algebra is not possible, and this is the extension of other supersymmetric charges. And thank you so much. Please visit my poster presentation for more details. Thank you.
I'm Yuta Nagoya from Osaka University in Japan. My poster is about work in progress in collaboration with Masataka Koide and Satoshi Yamaguchi. Recently, there are active studies on generalized global symmetries and these applications. One of the directions is non-invertible symmetry. We investigate applications of non-invertible symmetry to 4-dimensional quantum field theory with a boundary. Especially, we calculate a ratio between hemisphere partition functions with some boundary condition in 4-dimensional lattice gauge theory. This quantity have information about denormalization group flows. That's all. Thank you.
Hi, can you hear me? Hi, my name is Hugo, and I'm from the Guangzhou Institute of Science and Technology. And in my poster, I will tell you about Krylov complexity for free and interacting quantum field theories. Now, Krylov complexity is a quantity that was recently introduced to study quantum chaos. And it's a notion of operator growth, which has been shown to probe chaos in quantum many-body systems. And the question is whether this quantity is also useful in QFTs. Now, in my work, which has been done in collaboration with these wonderful people here, including Mitsuhiro, who is presenting another poster, we studied the effects of mass, hard and smooth ultraviolet cutoffs, and one-loop perturbations to this Krylov complexity, and we studied the effects that these quantities have. And if you're interested in hearing more, please come visit me in the poster. It's right next to the water dispenser. Thank you.
Hello. Hello, everyone. I'm Norton Lee from IBS CGP. So we all know this AGT correspondence gives a connection between two-dimensional conformal field theory and four-dimensional n equals to 2 supersymmetric theory. So what we do is we propose a playground. We look at some defect in the n equals to 2 four-dimensional system. Actually, we introduce 2 of them, and we try to identify them as 5-point conformal block of this SLN current algebra. And depending on how the two defects are aligned, actually we got 2 different 5-point. And we also look into this relation with the XXX spin chain. So we're establishing the relation between 3 theories, supersymmetric gauge theory, CFT, and integrable system. Thank you very much.
Hello, I'm Satsuki Nishimura at Kyushu University in Japan. Today, my poster introduced our research in such title. Supersymmetric extensions of standard model often have baryon number or left number breaking terms. One of the famous example is proton decay, but no experiments found this process. So theoretical works should suppress those. So to do this, we use the modular symmetry and classify the supersymmetric theory. In my poster, I focus on the minimal supersymmetric theory, and using integer weight, we found this R parity. I'm looking forward to talk with you. Thank you.
Hello. Hi, everyone. I'm Devarshi Vasu from IIT Kanpur, India. And my talk is about reflected entropy in holographic moving mirrors. So, next slide. Yeah. So, moving mirrors are boundary conformal field theories with a moving boundary, accelerating boundary, which radiates and mimic black hole radiation. And we compute the reflected entropy, both field theoretically and holographically through the entanglement wedge cross section in the dual plane wave geometries truncated by an end of the world brane. And this is one example of the holographic result where the entanglement wedge cross section lands on the end of the world brane, and this is the answer for it. And we also plot the pH curves for the reflected entropy and we have found this thing matches with similar results in the literature. Thank you, and visit my poster for more stuff.
Hello everyone, I am Vinayak from IIT Kanpur. So there are 2 main ingredients in my work here. One is entanglement negativity, which is a mixed state entanglement measure, which have this form of quantum information theoretic definition. Recently, an island formula for entanglement negativity was also provided, which is of this form. And the another ingredient, sorry, it was previous slide itself. So the another ingredient is the defect extremal surface, which is an extension of the usual ADS BCFT setup, where we have a defect conformal matter living on this end of the world brane Q itself. Next slide, please. So in this work, we provide a doubly holographic frame expression for the island formula for entanglement negativity, and we compute different this entanglement negativity for different mixed states. One example is this, where we have subsystems in 2 radiation bars, RL and RR, and there are 2 possible phases possible here. One have no island, and another has an island contribution this part, and we have obtained the page graph of this form in this case. Thank you.
Hello everyone, I'm Yusuke Taki from YITP in Japan. This is based on 2 different projects. Please, next slide. DSCC correspondence is an example of the Dosita holography, but this has many puzzles to be solved. This presentation is based on two different works, and one is about the description of the dual CFT by using a special type of conformal field theory called SU2 similarity model. The other one is the discussion on the extension of the Ryu-Takayanagi formula to the CFT correspondence. We claim that by using the generalized notion of the entanglement entropy called pseudo entropy, the holographic relation analogous to entanglement entropy holds. Thank you very much.
Hello, everyone. I'm Wei Guang from University of Tokyo, Kavli PMU. My work is about boson fermion duality with subsystem symmetries. Motivation, similar to Stephen, we are interested in fractal models. In some models, single fractal cannot move, but dipole can move. And usually, it comes with gauging subsystem symmetries. And such models have some Foliesian structures, which we can use similar to the ordinary global symmetries. So we generalize the 1 plus 1D boson fermion dualities to 2 plus 1D with subsystem symmetries, and which can help us to get more fermionic subsystem symmetries. And main result is we find the exact dualities in lattice models with Z2 subsystem symmetries by a so-called generalized Jordan-Wagner transformations, which just the Jordan-Wagner strings winding around one spatial directions. So it can be extended to 8 different transformations, so we get a huge duality webs. So thank you. Yeah.
Hello everyone, I'm Naoki Amori from KK, Sokendai, Japan. So I'll talk about the non-perturbative approach of superstring theory and obstacle of simulation. So the IKKT matrix model is the most promising candidate for non-perturbative formalism for string theory, which is expected to solve like these problems based from perturbative formalism. In addition, this model has attractive property, also which is the space-time that emerges from dynamically of degrees of freedom. Please, next page. However, when we simulate this model, so the sign formalism happens because of the oscillation of the imaginary part of the action. So to solve this, we applied the Lefschetz simple method to this model, and I will talk about the result of application of this method and talk about the emergence of real space-time. Thank you.
Hello, I'm Shivam from ICTS India, and I'm going to talk about how to formulate real-time holography in special cases where we suddenly change the temperature from T1 to T2, let's say. And the more specific question we are asking, how to find real-time correlators in an holographic CFT under thermal quench. The gravitational dual picture we have is the following. Suppose we have a black hole in asymptotically ADS background with an infalling shock wave, which converts the black hole with some horizon into another size of horizon, changing the temperature from T1 to T2. And if you can, yeah. We have solved this problem by proposing a holographic, by gravitational dual of this CFT in the Schwinger-Keldysh formulation. And I have told you the problem, but for the solutions, I think you have to go out and check my posters. Thank you.
Hello. Hello, Brian. We studied quantum quench in this Gauss-Nebu model. This is a massless fermion and with quartic interaction with many flavors theory. And under this transformation, the symmetry breaks down and and fermion get mass, but at 0 temperature. But when temperature is above the critical temperature, the symmetry gets restored. However, we study quantum quench in this model by changing the coupling, and we have seen that the time-dependent fermionic mass goes to zero, and which signals that some effective notion of temperature, which emerges here. Next slide. We also study some critical dynamics in this theory. So when the coupling approaches some critical point, It shows some critical dynamics, and I will tell more detail about in my poster. Thank you.
Yeah, hi. I'm Anurag from IIT Kanpur, and I'll be discussing about this wormhole and half wormhole under relevant deformations in SYK one-time and two-time toy model. Next slide, please. So basically, our objective is to study the existence of this wormhole and half wormhole saddles in the irrelevantly deformed one-time and two-time SYK model, and how the factorization problem gets restored, which is basically if you have two disconnected boundaries here, L and R, and you have an answer from CFT which factorizes because they are disconnected, and you have a gravity, now you have a gravity dual which explicitly connects these two, which does not factorize. So how this gets restored through these two type of saddles? We find that in the irrelevantly deformed theory, both of saddles exist, and they lead to this resolution of the factorization problem. And the second point is this deformation can be thought of as a renormalization of the coupling. And we also studied the two-time case, which has a non-trivial dynamics of the saddles. For more details, please take a look at my poster. Thank you.
Hi, I'll talk about asymptotic symmetries in higher dimension. I'm from ICTS. I'm Chandramouli. And the basic question that we are interested in is the symmetries of GR at null infinity in flat space-time. And what is found is that the symmetry group is larger than the Poincare group. And the way you find it is that you just solve this equation order by order in R. And depending on that, you allow for your killing vectors. And and then using that, you can find the space-time action in various fields. And I'll just summarize the results. There are more details in my poster outside. So what we have been able to do is compute the charges corresponding to these symmetries in nonlinear GR. And we have been able to relate them with soft theorems and memory effect in higher dimensions for both supertranslation and superrotations. Thank you.
Hello everyone, I am Hiroki Wada from Osaka University in Japan. In the last 10 years, new types of symmetries, so-called generalized symmetries, are used to study quantum field theories. Our work is motivated by the following question: how much can we extract the dynamics of strongly coupled theories by using such recent developments? Next, please. To this end, we consider the linear quiver gauge theories depicted by such a quiver diagram. Because their coupling constants are strong at IR regime, it is our task to specify the IR description of our theories. Then we investigate the IR effective theory of our theory by the argument of the anomaly matching condition. Thank you, that's all.
Hello, I am Minhajul Islam from IIT Kanpur. I will talk about Galilean gauge theories. Next. So, among different types of non-relativistic conformal symmetries, our main focus is Galilean conformal symmetry and Schrodinger symmetry, and see this symmetry at the level of non-relativistic Lagrangian, where we get this non-relativistic Lagrangian from one higher dimensional relativistic theory. First, we check that Galilean electrodynamics and this Galilean Yang-Mills Lagrangians are infinite dimensional Galilean conformal symmetry in 4D and infinite dimensional Schrodinger symmetry in 3D. And also in Galilean electrodynamics, how this electromagnetic duality we can see, we have realized that. And at the end, we have given that all Feynman rules for pure Yang-Mills theory to study the quantum structure details in further. For details interested, come to my poster. Thank you.
Hello, my name is Motokazu Abe, belonging to Kyushu University in Japan. I talk about fractional topological charge in lattice abelian gauge theory. Recently, Gayat et al. Has discussed new types of anomaly, which is related to higher form and discrete symmetries. And we concentrate on SUN gauge theory with that term, and it has mixed new types of mixed anomaly. And the fractional topological charge is crucial for this anomaly. And then our motivation is to understand this anomaly and fractional topological charge in a completely regularized framework, lattice field theory. Next page, please. Then we constructed the transition function on the lattice U1 over ZQ gauge theory. And our construction provides the mixed Hooft anomaly between the ZQ1 form gauge theory and asymmetry and the time reversal symmetry when theta equal to pi. That's all. Thank you.
Hi everyone, I'm Kajal Singh from HRI India. I'll talk about our recent work on joint distribution of cosmological constant and the gravitational mass, which sets the scale of supersymmetry breaking. This is done in the setup of flux vacua of type 2b theory. Building on previous works where it was assumed that near the zero cosmological constant, what happens is that the distribution of supersymmetry breaking scale basically decouples from the total distribution, and that leads to the density function having a preference for higher supersymmetry breaking scale. We tried to basically produce this result by incorporating two key ingredients, which is the moduli stabilization and uplift sector. So in our explicit calculation, what we do is we add the uplift sector from coming from the anti-D3 brane uplift in nilpotent superfield formalism. And what we find, in contrary to previous results, that the density function basically prefer a smaller value of supersymmetry breaking scale near very small value of cosmological constant, where you can see the density function is highly suppressed in terms of the gravitational mass. Is it done? Okay, thank you. Please check out my poster for more details.
Okay. So hello everyone, I'm Junsei Tokuda from IBS. This work is in collaboration with Toshifumi Naomi in Kobe University. The main motivation of this work is to derive the swampland conditions. And in the absence of gravity, it has been long known that the swampland-like bounds exist. Such bounds are so-called positivity bounds, which are derived from S-matrix unitarity, analyticity, and so on. And if such bounds are also applicable to gravitational theories, we can obtain interesting bounds, such as weak gravity conjectures. And 2 years ago, Simon Caron-Watt and their collaborators proposed a clean way to derive a positivity bounds with gravity, but unfortunately, their method suffers from infrared divergences in 4 spacetime dimensions. So we propose another method to derive IR finite gravitational positivity bounds in 4 spacetime dimensions. And our formulation is based on the finite energy sum rules and crossing symmetry. So thanks for your attention.
Hello everyone, this is Zhou Jianyu, and I'm from Sokendai in Japan. And this work is about the numerical study of quantum cosmology. And the main motivation of quantum cosmology comes from the two proposals that describe the universe starting from nothing. And our main purpose of this work is to try to find a way to implement first principle calculation on this topic so that we can answer such questions as which proposals is true or more natural in the future. Next, please. And our main result on the bottom shows some important feature of different proposals, different saddle points, and different geometries in these plots. And we find that we can acquire this with suitable numerical tools and correct simulation setups. And we believe that with this ability, we can find more important and interesting physical significance beyond simple model and beyond classical predictions. Thank you.
Hello, I'm Unu Lee from Seoul National University. I want to talk about how to understand black hole microstates in anti-de-Sitter space in terms of giant gravitons. To do this, we studied superconformal index of n equals 4 Youngmills in order to account for the entropy of the dual black holes in anti-de-Sitter space. In particular, we used a newly suggested giant graviton expansion formula for the index of the super Yang-Mills, where the index is rephrased as the expansion in the giant graviton numbers. We counted giant graviton states using the index and reproduced the entropy of the small black holes. which shows that the small black holes in ADS can be viewed as hadronic excitations in the confined phase of gauge theory. So if you're interested in, please come to my poster. Thank you.
Hello everyone, I am Trakshu from TFR Mumbai. Today I will talk about multipartite entangled measures, their classification and holographic duals. Next slide. Yeah, so a q-partite entangled measure is the information contained in a q-partite quantum state that is invariant under local unitary transformation. So there exists special class of measures called LM measures that can be computed holographically using liquid small decision techniques. So the goal is to characterize all the LM measures, and the result is that the characterization of LM measures reduces to the characterization of finite abelian groups. Next slide, please. So we define a rich subclass of all LM measures that we call generalized multi-entropy, and it is parameterized by q integers. And for CFTs with large central charge, this can be computed holographically as the minimal area of a weighted soap film web in the bulk. And each film is weighted by the tension that is given in as the log of the LCM of MAMB. And so thank you, and for more details, please visit my poster, and I'll help you discuss.
Hello everyone, I am Anashri from IIT Guwahati, India. So I will discuss about this pole skipping with scalar cosmology interaction term. So pole skipping is a method to predict this chaos Lyapunov exponent butterfly velocity from energy density 2-point Green's function. So at specific values of frequency and momentum, the bulk linearist differential equations have multiple solutions at the horizon, and that leads to some non-unique Green's function at the boundary. So in my work, I have done this metric perturbation, which you can decouple to shear channel and sound channel. Next slide, please. In this specific model, and the background is this Schwarzschild ADS4 background. And the shear modes and doing the shear mode analysis, we got some correction to this momentum value. And doing this sound mode analysis, we got this chaos values, like this Lyapunov and butterfly, where we didn't get any correction. From this temporal component of this Einstein equation, you can see this lambda and PB. And from the singularity analysis of the master equation also, you can check these points. So please come to my poster to have a better overview of this result.
Hello. So welcome everyone. So in this work, we find the new eigenmodes of modular Hamiltonian of a CFT in the vacuum, and we show that they satisfy the Virasoro algebra. So you know that the modular Hamiltonian for a subregion is defined in this way, and the total modular Hamiltonian is the difference of the modular Hamiltonian of the region and its subregion. For the ground state of CFT, the expression of the modular Hamiltonian is known, and previously it was known that the OP blocks of any two primary operators is one of the examples of modular eigenmodes, and the spins difference of the two operators being the eigenvalue. Next slide. So in this paper, what we do is that we construct another infinite class of eigenmodes that look like this, and the anti-holomorphic part is also there, and we show that these eigenmodes, along with the modular Hamiltonian, satisfy Virasoro algebra. And we have also shown that for certain choice of this constant n, the global part of the algebra can be interpreted as the modular Hamiltonian, and if we divide the modular Hamiltonian in two regions, then okay. So if for details, come to my poster.
So motivated by the fastball geometries, we have constructed a very simple toy model by placing a cutoff at the stretched horizon in the BTG geometry, which is very similar to the particle in a box problem. And then we quantize a scalar field in this geometry, which will give rise to normal modes. Now, if you plot the spectral form factor of those normal modes, you can see a clear evidence of deep ramp Plato structure with a ramp of slope 1, which is a feature of random matrix theory. And this non-triviality, I mean this deep ramp Plato structure is actually coming from the J direction. So the J direction is very crucial to get this deep ramp Plato structure. And the last image is the random average version of the previous image, where you can see the clear slope 1 line So that's all. So thank you, and please do visit my poster for further information.
Okay, that's all for the Gong Show. So I'd like to thank everyone for staying until the last talk, and let's thank all the Gong Show presenters.
Okay, so there will be a picture, and also you can approach the poster presenters, and also poster will be there until I guess 2 days later. I think we have one day afternoon, which is free in maybe Thursday or Friday. Yeah, Thursday. Then we can all hang around a little more and see the Gongshu and the poster sessions and talk to the poster presenters. Thank you.
뭐 이거 그냥 놔두면 이거랑